Hello grade 12s, welcome to my channel, and I hope you are all in good spirits and some of you have started writing, I believe. Let's just keep going and hopefully you guys are going to be enjoying these revision lessons. Again, it's one of the specials. I personally wrote this paper in my finals, so this ends the nostalgic rants, isn't it? So yeah, that is the story right here. So general instructions, nothing really out of the ordinary, pretty intense stuff, but there were some changes on resistors, so we used these from these ones. Our resistors were usually shown like that, and the light bulb was shown like this, and then it changed to that. So those were the two changes we noticed. Otherwise, marks will be forfeited if instructions are not followed. So remember this, guys. If you don't follow the instructions, even if you do the right thing, you lose marks. Even the numbering of questions, if you don't number them according to the specifications in the instructions, you end up with a mark lost for that particular question. It did not number properly. Be very careful. Marks are not just lost by messing up the entire question. They can be messed up from just not following instructions. Now let's look at instructions for question 1. Again, this one doesn't really have much, but to just emphasize the fact that there's only one answer for one question. Sometimes there is a catch to check if you understood this instruction. There may be 2 or 3 correct answers, but please choose one. But most of the time, if there's 3 possibilities, it means the best one needs to be chosen, usually. Okay, guys, that's it. Let's not complicate this. It's pretty straightforward. Let's look at the questions. Question 1.1 says, 2 forces, a 10 Newton force and a 15 Newton force, act at an angle at the same point. So this means these 2 angles are at some angle to each other. And normally we use theta to suggest any variable angle. Beta can be used, alpha can be used, okay? Now, the question says, which one of the following cannot, meaning we want the wrong answer, be the resultant force of these 2 forces? So what does the resultant mean? By definition, we know the resultant is a single vector that will have the same effect as 2 or more forces acting together at a point. Okay, so that's the most important. Please revise definitions. They are examinable. Now, guys, when do we exclude or include possibilities? Because we've got lots of possibilities. Obviously, we need to focus on the range of answers. The range is such that we have a maximum, which will occur when theta is 0 degrees, meaning these forces are acting at a point together like this. This is the point. This is the tail. Head to tail method, if you think about it. So we've got the 15 Newton force, 10 Newton force, and the resultant force, R, is going to be the summation of these 2, which is 25, sorry. Okay, that would be the maximum value. Now, what would be the minimum value of our resultant force? It will occur when theta is exactly 180 degrees between these 2 forces, so that these forces oppose each other directly. So we've got the 10 Newton force, we've got the 15 Newton force, and our resultant is going to be in the direction of the bigger force, but we take the difference. So 15 minus 10 is going to be 5 newtons. That would be the resultant R. Okay, so anything outside this range is not possible. And what do we see? 2 is outside the range, meaning it's impossible for these two vectors to have a resultant force that is that. But this one is the minimum value. Yes, this one is in between. This one is in between. So these are within the range. And this one is outside the range. Okay, so very important. So we are choosing the wrong answer, and the wrong answer is the right answer. Okay, easy stuff. I've explained this this question before, so please trust me. If you are a true what can I call it? If you're a true science student, meaning you're doing maths and physics, you should be watching every video I post, even for grade 10s, because I post stuff that is relevant for grade 12s as well, including grade 11s. Okay, so this question transcends those 3 grades. Now, a body of mass m is held at rest. But now, what do we know about the word rest in physics? It means a state of equilibrium. That's the correct word to use. And equilibrium means the resultant force is 0. And it also suggests that there is no acceleration in the system. And the word rest literally, it also means the initial velocity is 0, meaning we are not moving at all. Okay, that's the most important. It's held at rest by a light inelastic cord, PQR. We can see PQR, okay? Now, what do we know about light? It means light is not adding any mass into the system, and it is inelastic, so that if there's movement here, everything moves at the same rate. And essentially, if we measure the tension between any 2 points, or a tension at any point on that cord, it should be the same. Okay, great. So what does that mean? This means this tension F here should be the same as the tension on the other side. Okay, that's the idea given here. Now this passes over a smooth peg. Again, the smooth peg says there's no friction. Essentially, the tension on either side of this peg should be the same, meaning the same thing. Now, section PQ of the cord forms an angle. Now we can see this question mark is meant to be theta with the vertical section of the cord. Okay, that's easy. Question says the magnitude of force F, which keeps the system in equilibrium. If it keeps the system in equilibrium, it is itself an equilibriant. Okay, nice. Do you see that equilibrium came? There it is. Now we need to find the value of this force M, but now we're using mass M as our reference mass. So if we draw what we call a free body diagram, there's 2 forces acting. It's going to be force F, which is the tension on that string, and the gravitational force. But if this body is at rest, it means the resultant force is equal to 0. And for the resultant to be 0, this means these 2 forces must be balanced. So what do we know? Fg is m times gravitational acceleration, and that should be the same value. So that defines our force F. So it becomes mg. So this question needs one to understand what is given, to see how to relate everything to one another, and to answer the question adequately. So that's how that one goes. Now 1.3 says a ball is thrown vertically upwards. If we're throwing it, we're giving it initial velocity, meaning it is equal to some x value. It's not 0. That's the idea. And it is being thrown vertically upwards from a point and then caught at that same height when it returns. Okay, so this is giving us an impression of a projectile. Okay, but be very careful. We were not told to ignore effects of a friction yet. So we may not necessarily be looking at a projectile, but the topic that we understand in grade 12, this would suggest a projectile. And what is a projectile? It's an object or a body that is given initial velocity, then subsequently undergoes motion influenced by the gravitational force only. Okay, that is the idea that is somewhat being given to us, but we cannot say for sure. Now the question says this is thrown at some point and then it comes back to the same position. So let's just consider this a bit more. Say this is the ball and we are throwing it upward. It reaches maximum height, then comes back to the same position it was thrown. Okay, so this is the story. So the ball goes up and we know that it has some initial velocity, but the final velocity at the highest point is 0. And then as it comes down, it gets the same velocity, but it's negative. That's the idea. At that same position, it will reach the same velocity that it left that position with, but it will be negative because now it's in the opposite direction. Remember, these are vectors, so this is what we need to think about. And obviously, if this is projectile motion, we understand that acceleration is basically g, and g is always downwards. Okay, this is if we are dealing with a projectile. We are not sure, we will see. Now it says which one of the following velocity time graphs. Now there's a few things that we need to really be careful about. Now a velocity time graph, there's 3 things we need to understand. The gradient represents acceleration, and then we know that the area under the curve represents displacement. Okay, and then of course you guys talk about position at times. Okay, not a big deal. So in a velocity versus time graph, we need to consider those 2 things as well. Now we're saying which one of these graphs is the best representation of the situation. Remember, best does not mean the correct representation, but it means it's better than whatever else is here. So this is very important. We could be dealing with a projectile, yes or no, we don't know. But we have to select something that speaks sense in the given scenario. Now we can see that this graph starts at 0, but remember we knew that the velocity was not 0 because this was thrown, so it has some value to it. It can't start at 0, so that's not correct. This one cannot start at 0 either because we saw that this was thrown, meaning there is some initial velocity. But this one says yes, we are starting at some velocity, whatever value it is. And this one also says we are starting at some velocity. So this is good. And for these 2 graphs, we're already indicating that upward was taken as positive, because we can see this is starting above the t-axis, and that's positive. This one is lying because it says we're starting at 0, so it's not good. Right. And then we go on and say at the very top, the maximum height, the velocity is 0. So it is not a positive value. It can't be. But this one is correct and that one is correct because there we have 0 velocity there. It's on the 0 mark, the baseline. Great. Now, at the very end, when it gets caught, it has caught up with the same velocity but in the opposite direction. So this one is good, but this one is wrong because it's saying the final velocity when it gets caught. It's actually the same in magnitude and direction. Remember, this is a velocity time graph. Velocity is a vector, so direction is important. It's not just a speed. Don't here. So this is good. And there's 2 reasons why essentially this is wrong. If we're saying, okay, now we can appreciate that this is more of a projectile motion because we can see the gradient is somewhat constant. This one is not constant. But for a projectile motion, we know gravitational acceleration is the same value downward. And this is a negative gradient. And it's constant. And this one is changing. It's not constant. Already the gradient is wrong, whereas the gradient here is correct. So this is definitely the best representation of this motion. And indeed, it confirms we are dealing with projectile motion. At least, it is best for that scenario. So be very careful. Certain statements need you to thread carefully before you pick your choice. Okay. Now, let's have a look here. It says now, 1.4, it says the equation of motion S. Now, you don't know what S is, guys. S is basically displacement. It meant what you guys call delta X or delta Y. But specifically delta Y, because normally we deal with vertical projectile motion in grade 12. Although we cannot ignore this for grade 12, because some questions we have linear motion anyway in the horizontal plane. So we can still consider this as delta X, but mainly we look at it as delta Y. Now we're saying this can be represented by the following velocity time graph. Remember, what do we know about the velocity time graph? We know two things. The gradient gives us acceleration. The area gives us displacement. Okay. Very important things to remember. Okay, now this is the velocity time graph. We can see here that there's u. U is basically this unit from 0 to u. Right? Right. And then here we can have t units, basically, because this is time. That's what we have. And obviously that one too represents our velocity there. Okay, that's very important. Now, this would be initial velocity because, again, let me just introduce this. I liked this notation of our equations of motion because it keeps things clean. This VI, VF nonsense makes it very complicated and dirty anyway. So I don't know how you achieve neatness when you have such a nonsense being propagated and propelled, and in fact, proudly so. Anyway, whatever. Now let's have a look. This was better because if you're considering two objects, now it would be easy to say U sub A for object A and U sub B for object B, especially for momentum calculations, where you have subscripts to denote two different objects, but in the same system. Now this VI nonsense creates two subscripts at a go, and that's not quite good because a subscript, ideally, it's better when it's just one, not two. But anyway, whatever, guys. I cannot change how things have changed for the West, perhaps. Maybe not. Maybe I'm crazy. Let's leave it at that. All right, guys. So this is what we have. So U there represents that. Okay, so those are just the two things to consider. Otherwise, the rest is the same. Okay, now it says the quantity half 80 squared in the equation is it area P plus Q? Is it area P alone? Is it area Q? Is it area Q minus area P? Now, if we're looking at area Q, we can see this is a rectangle. This is a rectangle. And this area Q is literally length times breadth to find the area. And length times breadth, length is T here, multiplied by the breadth is going to be that unit U. So this is basically UT. So area Q is basically the UT component. So obviously the remainder is going to be area P, because we know that the area of a triangle is half base times height. Right. Although this is complicated, we don't really care for this to give us half 80 squared per se. All we know is that if we ignore the half, base is time times height. It's going to be the difference in those velocities. The velocities are in meter per second or meter per unit time. The times cancel, and what remains is meters, meaning it's still displacement. So that is how I look at it holistically, guys. So sometimes you just have to look at things and understand them from just the perspective being propagated in a particular question and get the right answer. So here we don't need to look any further. We can just get our answer nicely and we move on. So I hope you are understanding how things work here. 1.5 says a box of mass m rests on the floor of a lift which is accelerating upwards. So we've got a lift here and we've got a box in the m, and the lift is accelerating upwards at acceleration a. The lift's acceleration is a, and the acceleration due to gravity is g. Not a big deal. Now, if this box is resting on the floor, it means it is itself accelerating at acceleration a, because they are together, they are combined, so they will accelerate with the same acceleration. Now the question says the resultant force. Again, it's underlined. The resultant force on the box is equal to, now this is basically Newton's second law. Nothing but Newton's second law definition. Now, what is Newton's second law? It says the resultant force is equal to mass times acceleration. So the mass is m, acceleration is a, so that is correct. So this is just a way of asking the definition in a smart way. You are given stories to get confused. At the end of the day, you have to give an answer because this is the definition of the resultant force according to Newton's second law. So this is just to assess one's understanding of the law. Easy. Again, it's a very easy mark for a student who knows their work, but this could be a nightmare for someone who doesn't. Okay. Okay, so that is essentially easy. So again, sometimes you get a relief, but a very strange relief. It could actually take you down if you're not aware. Now, 1.6 says, Aziz sets out on a journey to the moon, okay, in a spacecraft. Now, the gravitational force of attraction, that's nothing but the weight of the Earth on him while he is on the surface of the Earth is F. So this simply means F is big G, M Earth, M of Aziz, all of this divided by the radius of the Earth squared. Okay, so there is our Earth, there is the center, so there is the spacecraft, whatever that is. It looks strange anyway. And Aziz is inside, so the distance between these two is the radius of the Earth, r. Okay, now we are told what would be the gravitational force of the Earth on Aziz if he is at a height equal to the diameter of the Earth above the surface of the Earth. So now Aziz is sitting up there. Okay, so there is Aziz and his lovely spacecraft, strange as it looks, and he is there. Yeah, this one didn't come out nicely. Anyway, he is sitting there, and we are told that this distance from the surface of the Earth is 2 times the radius, because the diameter is basically 2r. So this means his distance from the center of the Earth is 3r, because we are adding those distances. Nice and easy. So what would be the force? Now we know that, okay, we want to know this force in question. It's going to be G M Earth M Aziz divided by, now this is 3r squared, sorry, 3r all squared. This is G M Earth M of Aziz divided by, now this goes to 9r squared. But if we want to compare it to the initial force, F, we then need to factor out this 1 over 9 into G M Earth M of Aziz divided by r squared. And we can see this is nothing but 1 over 9 F, because this represents the force F. So we simply substitute like that. So simplifying algebraic expressions, we can get an understanding of what direction they take. So this one is very simple. It's option C. Again, this is something you don't want to bother with the rest of these others, because you have to work it out. There's no guessing the answer here. Obviously, this is me trying to show you if you don't know what to do. But a student who understands this topic would not even need this calculation, would just know in their brain, this is 3r squared. So 3r all squared, which becomes 9r squared. Therefore, you factor out the 1/9, then you get F. So they'll just jump for that answer in a moment. But to convince yourself if you are doing the right thing, this is best, because as you proceed, you know this answer is correct. There's no saying, I'm not sure. Please perform the necessary calculations so that as you move forward, you know I'm getting those marks. Okay, 3 separate identical balls. Now this word often creates confusion, because in what regard are they identical? Well, usually we're talking about the spherical space that they contain, meaning their volume. Usually that's the identical nature. Maybe size, we can say, diameter, whatever. That is what it means. But be very careful. Maybe we can even include mass, but be very careful again. Sometimes in physics you get this word identical thrown loosely, and yet it doesn't mean everything is equal, but it means certain things are of equal measure. Okay, are in contact with each other in a straight line, okay, and are at rest. How many? 3. So it's these ones. On a smooth horizontal surface, meaning no friction. Now each of these balls has mass m. Okay, we can see that it's indicated. Another ball of the same size, do you see that? But of a different mass. Okay, moving at a velocity v, collides elastically. Now what do we mean by an elastic collision? It means EK taught before collision must be equal to EK taught after collision. So that is conservation of kinetic energy. That's it. So this question is based on that, in momentum, energy, and power, whatever. Okay, it says now, and in the same straight line with the 3 stationary balls. Okay, not a problem. Now, which one of the following diagrams represents the situation immediately after collision? So that means EK before, total EK before has to be equal to the total EK after. So let's just say before collision, the EK taught is going to be half mv squared plus half mv squared. Now this is half, this one is 2m, velocity is v all squared plus half, this one is 3m, okay, I'm running out of space, So 3m, the velocity is 0. So this is nothing but, now this 2 and that 2 do the things, so we end up with mv squared plus 0. This is mv squared. So the total kinetic energy of the system before collision is this. And remember, there's no friction to dissipate any forces here. Now this means we need to look for a scenario here that gives us that total kinetic energy. Okay, so if we look at the first, we will see that this is now 0, so we don't worry about it, so we focus on this. Okay, again, know what battles to fight. Don't waste your time calculating there. This is going to be essentially half of m times 2v all squared. That's going to be 4v. 4 divided by 2 is 2. So we get 2mv squared. So this one gives us 2mv squared, and that's not the answer. And then, so anything that goes to rest, it's not to be worried about. So if you look here, what do we get? We just simply get half mv squared, and that's not correct. And then again, we're looking at the moving part because we know the other one is going to be 0. What do we have here? We get half 2m into 2v squared. So what does this give us? It gives us this, and that cancels. This essentially gives us 4mv squared, and that's not true. Obviously, this one should be the answer. If all the others are failing, they will pass. This one is half, m is 2m, v is like that, and that cancels, so we end up with just mv squared. Can you see that? That is the same thing as that. So that is essentially a question. I mean, questions on momentum are very easy as long as you understand the question and you know where to look to answer the question, because again, if you guys have eyes all over the place, you will end up lost, believe me. Anyway, let's have a look at the next question. It says that physical quantity energy expressed in base units is, so now what is energy, guys? It's work, right? Work is basically in physics the resultant force multiplied by the displacement. Tinage, we used Fs, but you guys are using work is equal to F net, I hate that word, I don't know why, multiplied by delta x cos theta. But again, this cos theta is just to show that this is a vector. It's not just any distance. And yet displacement carries the same weight, but just too much in the formula is ridiculous in my opinion. But of course, the catch was that one would be caught out if they're not sure this is a displacement rather than just mere distance. Although this is itself a scalar quantity, but you can see vectors are at play here. Nice. Now, what do we know? We know that the force is in kilograms times meter over second squared, because it's mass times acceleration. This is multiplied by meters, because remember, delta x is a distance in meters. Cos theta is a ratio, there's no units, so it doesn't affect anything. It just changes the sign if necessary. So when we multiply, I mean, this is kg over 1, so numerators multiply, we get kg meters squared over second squared. This could also be written as kilogram meters squared per second squared, to try and use the notation in the question. Now, this is option B. Again, there's no need to waste time looking for others. Why are they not correct? Some questions are pretty straightforward, because if you have to perform a calculation, automatically everything else goes into the background. Okay, it stands away from the forefront. Okay, not a problem. Let's look at this question. See this one, I made a diagram there. Now it reveals where this connection is. Sometimes it's full of nonsense, this thing, but let's leave it alone. It's like this anyway. So it says a log of wood is attached to a cut by means of a light inelastic rope. So this rope means it will have tension. Okay, and the tension at any point on this rope is the same, basically, because this is inelastic. If the cut is moving, the log is going to move at the same rate as the cut, vice versa. Now a horse pulls the cut along a rough horizontal road. That means there is friction. Since these are moving, this is going to be Fk. Okay, with an applied force F. So we can see that force is this one. Now the total system accelerates. If it accelerates, what do we have? We've got a resultant force of some sort. It is equal to some x value. It's not zero. With the magnitude of acceleration A, okay, this is figure 1. Now the total forces acting on the cut during the acceleration are indicated in figure 2. Now here it's a mess. We don't know what is cooking here. But we can see, what is this? Earth on cut, we see friction, we see F1, F2, we see our force F. There it is again. But now let's just draw a free body diagram on the cut so that we can understand what is the story about this. We know that this force is the dominant force, is the force applied. Sometimes this tablet irritates me. There are some areas that just don't write so well. Like this one, can you see? That edge is poor. But it's because it's not clean. Anyhow, we will have a vertical force straight down, which is force of gravity, meaning the force of the earth on the damn thing. Excuse my expression. And we will have the force of the ground on the object, which is the normal force. And then we have tension, which is the force of the rope on the cut, right? And we will have frictional force. I don't know how big it is, but if we're accelerating, it's not that big. Fk, okay? So understanding this, we used a force diagram. We'd literally just draw the cut like that and still represent the forces. But you guys have replaced the object with a dot, so whatever. Now, we need to look at this thing. We can see that we can see the position of this earth on the cut. This is nothing but Fg. Okay, so this is suggesting that this is below this. So this is probably the line of axis. And then we see friction to the right. We see this force to the left. So this means the direction to the left, direction to the right. And at the bottom we have force of the earth. So at the top, this means this F2 should be normal force, isn't it? Because it's at the top, the very top here of these forces. And we've got F1. So essentially F1 here, since this is given as friction, this one should be the tension on the rope. That one should be the tension on the rope. So again, you can see this diagram is crazy. And in fact, this question gave me a bit of goosebumps. I jumped it because I couldn't figure out what is cooking here. Anyway, let's go on. Which one of the following combinations would be the most appropriate labels for F1 and F2? We can see that F1 is supposed to be the tension, meaning is the force on the rope on that cut, because rope means tension. So this is correct. This is correct because again on the rope it suggests tension. The force of the log on the cut. is interesting because guess what? What is responsible for this tension is this log on the cut. But essentially what is in contact with the cut right now is the rope, meaning the tension. So again, questions like this can cause a bit of a confusion because one would say, why not the log on the cut? Who is in contact directly with the cut? It's the rope, and the rope has tension. The tension is due to the log, but we look at the immediate bodies interacting. So this is force of the rope on the cut, suggesting tension. This is the best answer. Rather than that, this is also correct in a way if we didn't have this. If we had something else that is crazier, this would make sense. But this combination says this is the best representation of the force, which is the tension there. We can't go and look for the second object when there's already one immediately in contact with that. Even though that is influenced by the log, at this point, we're not interested in what is distant. We want what is close. This is why I hate that question where they say there's a book or a bucket on the table, and then all you're talking about is the force of the earth on that thing using the reaction or action-reaction pair. I hate that question because, in my opinion, it's controversial. Although the science behind it is correct, because the idea of action and reaction says you're acting at two separate bodies. These forces are acting at two separate bodies, not on the same body, which then becomes a bit sensible, but the scenario itself is pretty confusing. And in fact, I have my own ideas about it, but hey, I'm not the scientist, I'm just a fanatic, so let's leave it at that. Now, F2 is supposed to be the normal force, meaning it's the force of the rod on the cut. So basically, this is correct, and this is correct. This reaction force of the earth, it can't be. Okay, because we are told that the reaction force must not be on the same object. If the force is pulling the cut, then we have to see a force of the cut on the earth rather than on the same cut going up. So in a way, I want to accept that question, but okay, it's fine. Let's leave it at that. Some of the things are not clearly explained usually, so I don't understand certain things being just thrown at some point. But as you can see, that idea is as long as, you know, time. It's as old as time, not as long as time, but as old as time. So which one ticks all the boxes is option D. So this one was a strange question, trust me. The only reason I cracked it is when I did a force diagram. When I did a force diagram, so of course, Tinage, we used the object. Usually we'll just draw a box as opposed to just a dot. When I drew this, then I started to understand this alignment. This is at the bottom, should be there. Now that is on top, even though it's put on this side, but it's just there to confuse me. Then I know this is likely to be there, because remember it says best representation, doesn't mean correct. Okay, so this is very good. It's a very nice question, a typical higher grade question. Because no standard grade student can answer this question as easy as it looks. They would be confused as to what is cooking here, like I was initially. I mean, you wouldn't answer questions of this nature straight up. You need some work first. Okay, let's move on. A constant potential difference, constant potential difference is maintained across two parallel metal plates. Now, this is what constituted what we called the Millikan's experiment. This actually made us understand that an electron is negatively charged, because we didn't know if it was negatively charged or not. Okay, maybe let me not lie, but this is what emphasized, if not proved, that the electron is negatively charged. Okay. And of course, some say Faraday's work then got us the quantification of that charge, of course using some principles of quantum physics. You know such things by, say, Isaac Newton and many others. Oh yes, interesting, if not interesting. Now let's have a look, guys. We used to have this Millikan's experiment. We've got two plates. They don't really have to be of the same size. Then we connect them to a voltage source. Okay. So this is the long one, that is the short one. As we know that this is positive, this is negative, and this makes this plate negatively charged, and it makes that plate positively charged. Okay, so what happens? We are creating an electric field. Remember, the electric field pattern is from positive to negative, right? Nothing changes. Still the same, so the direction of the field created is in that manner. And of course, these plates are at a distance d apart. Okay, because the distance between the plates is d, and it can be varied, meaning we can increase it or decrease it. And as we would know, the closer these plates are together, the stronger is the electric field between them. And the far apart they are, if we increase the distance, the less will be the electrostatic, be the electric field strength between the two plates. Okay. Now, an electron in the space between the plates, of course, Millikan's use oil droplets. At one of the plates had a hole. Then they'll just put some few oil droplets and then observe in which direction they're going to move. And they saw that they tended to move towards the positive plate, to suggest that these are negatively charged. Okay. And that's how, whether it emphasized or it proved, I don't know, I don't remember anymore, but it had something to do with knowing the electron is negatively charged, essentially. Anyway, so let's place our electron there. Let's place our electron. So there is our electron. It's negatively charged. We place it there. And what is going to happen? We know that this is negatively charged. It should be attracted to the positive plate. Okay? In this electric field. Even though the field is going that way, it should be applying a force like that. But now, this is the force by the electric field, but this one is experiencing an electrostatic force upward. So this force is force F. So I hope the diagram is not getting a bit complicated. Because of its negatively charged nature, this electron will accelerate into the direction of the positive. So it means the electrostatic force of attraction is going to be greater than the electric field. The force by the electric field, which is going to try and pull it down together with its weight. Because now the free body diagram on that electron, it's going to be the electrostatic force to that positive plate, and then its weight straight down. But remember, the electric field is also downward. So this would be the force by the electric field as well. You see these things, very interesting. But again, if you look at this, the negative plate would repel this electron upward. So it gets a bit complicated. So the best way is just to focus on these two like that. So we know that this is Fg. So these things became very important for certain calculations regarding this, as you will see when we go ahead. And remember, I told you guys, MCQs are the window to those structured questions, and you will see why. Now, we understand this. Of course, we know that the electric field here is going to be the voltage potential difference per distance, which is going to be volts per meter. Okay, so that's the unit of the electric field strength there. When it comes to parallel plates, as much as we know the electric field is basically newtons per coulomb of charge, but now the force here, it's the electromotive force, meaning the EMF of this battery. Now that is measured in volts, but it's nothing but a force still. Anyway, it says now, which one of the following gives the relationship between F and D? Now we need to look at this question. This question is crazy. I'm just giving you the background here. But if we look at this, what do we know? We know that this is related to the electric field, isn't it? But now we want to know the force, the electrostatic force. So we know that the electrostatic force is basically the charge in coulombs of the electron involved multiplied by the electric field strength that or in which this electron is placed. Now we go on and simplify this and say our F, now the charge is that of an electron, it doesn't change. But what is E? Because it's parallel plates, we replace it with V over D. Right. And what do we notice here? We're told the potential difference is constant. So this means our formula is basically QV over D. And we can see that the charge doesn't change. The voltage doesn't change. That gives us a constant. Then we can explore the relationship between F and D. And we can see obviously that if D increases, F decreases because this is on the denominator. And if F increases, D decreases because this is on the denominator. And from here we can understand that F is actually directly proportional to 1 over D. Okay? When we keep the voltage and that charge constant, because that's the charge on an electron. And that spells out option D. But remember, for us to explore this relationship, something has to be a constant. If those things are changing, we will not see the relationship nicely. And if we want to explore this graphically, we can do it and say, well, this is how it is. If this is, we can decide what is where. We can put distance and force. We expect something like this. These are inversely proportional. Or we can do something like this and say this is 1 over D and then the force. Then we see something like that. Okay. So remember, all of these things, guys, need to be understood. Remember, when you are revising, don't just get to the answers and move on. Get to the answers and explore a little bit more so that your awareness is improved. You know what happened day before yesterday? I just decided to drive through one of the drive-thrus nearby just to buy some KFC. I just felt like an Khalili chicken. Drove there, came back. My driveway is a bit steep, okay? It's on an incline. So I parked the car in front of my garage. Now, I just pulled up my handbrake carelessly. I didn't notice if I pulled it strong enough to hold the car in position or not. I don't know. But all I know is that I pulled it as usual. Got out of the car, closed the gate behind the car. As I was moving towards the door, I just had a sound. Oh! Wow. And the next thing, my mind quickly clicked. This is probably the handbrake, because immediately after that I saw the car move. I was like, oh my God. It hit the damn gate. Of course, my mind, because I was not aware that this could happen. My car is not that heavy. I could hold it in position, or at least slow it down, so that even if we go towards the gate, I could be able to have a controlled movement until we get to the street, which is much straighter, and maybe get it to stop. But I didn't think of it. In my mind, I'm thinking of going inside the car and go and pull up the handbrake. But now I don't have enough time because I'm already behind the car. So I have to move away so that I don't get hit. So it hits the gate. While I'm trying to go around, then luckily my door was opened. So it got stuck on the gate, and that's how it got to stop. If I didn't, that car was going to drive below and go and hit the house below where I stay. And that would have been a disaster. I would lose my car completely. Because my pattern of thought at that moment, I didn't have time to think. I just needed to do the right thing, and the single right thing to do. It means for me, I needed to be aware of everything. And now that got me thinking, and I know the second time something like this happens, I get it right. This is what you gain from doing these exercises, because sometimes you do this, you get it wrong because you don't explore hard enough, but you think of many possibilities which can help you. When your brain is going through possibilities in a split second, you actually get, or maybe not necessarily not a split second, but in a moment, a few seconds, fewer than 10 seconds, you would have thought of the best way to control the situation, meaning to get the right answer. So this kind of thing of not just solving for the answer and move on, because you'll get stuck to one way of doing things. Like I'm saying, the one way of solving the car not rolling on an incline is to pull up the handbrake. But the damn thing failed. How could I prevent a disaster? If it happens that that thing fails, like in this case, you know how to just pick the answer, but now that way doesn't work anymore. You've got to explore options and even those proportionalities in their true sense. If you are to not modify the distance, what do you see? When you modify the distance, what do you see? You know? Then you get a similar question in the exam. You kill it in an instant. That is the essence of practicing. Sometimes you have to lose to gain. If you lose intermediately, it means for the finals, which matters the most, you will nail it. But anyway, guys, it depends on how you see these things anyway. Let's just move on before I spend too much time here. The centers of two identical metallic spheres, again, identical. In what sense? We don't care. Each carrying a charge Q, so they are identical in terms of the charge. Usually the volume in space would be the same. We cannot say the same about their masses. Are at distance, are apart. Okay? What I know is that these are charged spheres. So this is electrostatics. And now in electrostatics, we talk about Coulomb's law. And since these are of the same charge, it's just going to be Q squared over R squared. Okay? So this is just Coulomb's law. Now it says, which one of the following pairs of changes that are made simultaneously will double the electrical force? Is basically the electrostatic force that one charged sphere exerts on the other. Okay. So can you see, guys, a similar question to this one right here? So this should not be difficult. We apply the same approach, but again, it's going to take some calculations. Now, what happens when we decrease the distance by half? Remember, on the denominator of the formula, we will have half R all squared. This tells us that we still have our numerator as we know it. Now, this would mean this is 1 over 4 R squared of the same numerator. And this flips to the numerator, so we end up with 4 whatever numerator we had over the same denominator, and we know that that combination was F. So this would mean 4F, okay? Essentially, for now. But now we are doubling the charges on both spheres. If we're doubling, this is 2 by 2. That makes it 4. And now 4 by 4 gives us 16F. Can you see? So this one gives us 16F, and that's not what we want. Now, what happens when we do this? We decrease the distance by halving it, and we reduce the charge on one sphere. Now, that looks a bit strange. Let's explore it. Again, guys, some questions can be tedious. That's why you need to make sure easy ones you answer quickly, but these ones you take a bit of time. Now, we will have here F equals KQ squared over maybe let's not say Q squared as yet. We're going to have K Q1 times half of Q1, right? Because we're halving one of the spheres, but the distance is halved. Oops, why am I putting the square inside? Okay, let's see what happens. Now, we've got a half K Q1 squared over this one is going to be 1 over 4r squared, and the 4 goes and multiplies the numerator. We end up with 4 times a half kq squared all over r squared. Now this leaves a 2, so this is 2 of kq squared over r squared. This is 2 times f. Okay, so this one clicks. So again, you can see the examiners are very good in making this the second one so that you don't go through a lot of calculations, because if they decided to put it here, you would lose a lot of time. So sometimes the examiners are very friendly. How they organize their work helps to say, even if the student was going to faff around testing everything, immediately you hit the right answer. Don't go any further. Just stop there. It doesn't help to go further than that. All right, nice and easy. So that means the rest would be different, but you can explore what you get. Obviously they are wrong at this point. Now again, guys, I have a bit of a situation here because these things, yes. Okay, guys, so unfortunately some drawings are missing here, so I had to make up for them. Sometimes this thing shows me those lines, sometimes it doesn't. I don't know when does it do it, so I cannot predict it at all. I wish I could, because then I could take an advantage of that. Now we're told here a resistor is connected to a variable potential difference. Right. Yo, that's so small. Which one of the following graphs is the best representation of the relationship between the power P dissipated in the resistor as the potential difference V is varied? Okay, so what do we know? The formula that governs things here is that power is VI. But now we're talking about a resistor. We're not talking about the current per se. Now we need to change this one into power is basically because the current will change for the different potential differences. So we just want the variables to be alone and leave something constant, which is the resistor. So we know that basically V here, I is basically V over R. So always try to have some constant so that we can explore the relationship between two things. But the relationship must be between variables that we can see. Now if we look at this, it's going to be V squared over R. So this is the formula that governs things here. And if we like, we can even transform it to make it better and say P is 1 over R times V squared. Because this one makes it better. Because now we can appreciate that this is a constant because the resistance has not changed. That becomes a constant. Maybe let me write it in red so that there's no confusions. So guys, be in the habit to take a bit of time to figure out what is going on. When you see a graph, try to find an equation that can help to explain the changes according to the given scenario. Okay, because to use the current would not be appropriate here because we're talking about voltage versus power where there is resistance. We didn't speak about current because the current would change as well, so we can't use what would change. We can't have two variables changing if we want to assess the quality. We can't have two variables on this side that are themselves changing, and yet we want to explore the relationship between two other variables within the same equation. So here we need to keep those variables that are changing and keep the one that does not change. So that's why we do this. And we can appreciate that from this equation, we can see that as, P is directly proportional to V squared. Now this is essentially the relationship. And now this gives us the graph that we should pick. Now we can see that P is directly proportional to the square on the voltage. So it won't be this one, because can you see this V is not squared. But if we were to put a square, it would be correct. But now the square is missing, it's wrong. This one is definitely wrong. But can you see this is an exponential relationship, because as V increases, power exponentially rises because we are squaring the V. So this is the correct one. Okay. So again, if you understand exponential equations in terms of graphing them and what happens, you would understand this. Or even quadratics looked on the one side. For example, a basic quadratic, when we're looking at x values that are positive, this is similar to that. Okay, because the exponent is 2 there. So again, looking for analogies or similarities with what you already know, it makes life easy. This is why some people are never allowed to do physics if they don't do maths. As you can see, this is heavily mathematics, but this is nothing but a straight line equation. Not a straight line, but an exponential equation, essentially. Okay, this is the coefficient of that power itself. So its quality will tell us whether this appears above the horizontal asymptote or below the horizontal asymptote. Or we may even look at it and say, since there's no asymptote, because this one touches the 0 mark, so this is not necessarily an exponential, but this is a parabola when we're looking at the positive x values rather than the negative ones. So this is essentially a restricted parabola or parabolic relationship, which has some exponential nature to it, but it's not an exponential graph, because an exponential graph that is very basic would not touch the 0 mark. Can you see the understanding behind all of these things, guys? I know I'm stretching it, but I'm trying to give you as much as possible. I don't know what happened here, but yeah, something is missing. Okay, let's finish up quickly. Now, 2 heaters are connected to an extend A plug adapter. Now, remember, this is already spelling out parallel resistors, because the heaters are literally resistors. So this gives the idea of parallel resistors. Sometimes you may not understand what this is, but if you're talking about 2 things connected to an extend E plug, remember at home, the idea is that actually I never knew really what this is. And in fact, I'm not even sure today. But all I know is that at home, we connect our electricity in parallel. Otherwise, we would destroy the electricity if we were to combine things in series. So the connections is in parallel, and that's why when you overload, we call it an overload, but it actually decreases the resistance significantly when you connect too many resistors, such that the current becomes too high for the transformer or the whatever that thing is called, and therefore it falls because it senses an explosion can occur. Once the current is too high at the battery level or the transformer level, then the energy, the heat rises, and it can be enough to cause an explosion. That's why that circuit breaker will then cut off the power supply, the current to that particular resistor or plug where there's too many things connected in parallel. So this is the idea. Once you hear 2 heaters, think of home parallel resistors. Again, you may not be correct, but you will be guided by these possibilities and the scenario itself. Sometimes you're not sure, but you just think of something related to this, or that could be related to this. Now, when a 3rd heater, can you see we are adding more, is connected to the same plug, the circuit breaker cuts off the electricity supply to the plug. Can you see? It just goes off. Which one of the following statements explains the situation typical of when the resistance is too little and therefore necessitating an increment in the current enough to cause chaos at the battery level or at the whatever you call that thing at home, guys, for electricity? Now it says the potential difference across the circuit becomes too large. No. Remember, it's not going to change, because if we connect this to a particular potential difference, the EMF is the same, so nothing changes here. So not necessarily. The effective resistance increases. No, resistance does not increase but decreases. So already this is nonsensical. The effective resistance decreases, yes, and therefore the current becomes too large, yes. That is good. And this is what we understand. So already this one is the best answer already. The potential difference cannot change. I mean, think about it. What are you saying? Because there is not enough current. I mean, this is absolutely nonsense. What? It's absolutely nonsensical. So again, but be very cautious not to jump for the answer, because this might just be even better than that. So be careful. Before you jump to what seems to be correct, check if there's nothing better than that. Because here, it's a game of choosing the best answer over the correct answer per se. All right, easy stuff. Now, in the section of a circuit represented below, a potential difference is applied across x, y. See, usually the notation, can you see x is mentioned before y? So for me, it suggests that the current is in this direction from x to y, meaning x is the higher potential, y is the lower potential. And then, of course, the current, we know that it's going to split into these two currents that are slightly different. And then here they come together. And then they make up the same current again. So this is parallel connections. But now we need to be careful to look at these ones. These are in series with each other. So their effective resistance, or the combined resistance, is going to be 5 ohms. And these ones are also in series with each other. So we need to look at the total there. The total is going to be 10 ohms. Very important. This one is a simple question otherwise. But pay attention to the notation. Which of the following equations is true for current I2? So this is the question. I2. So now we need to understand the ratios and proportion. We know that the resistance ratio is going to be 5 ohms is to 10 ohms. Now we can say, okay, do we need to simplify this? Because look, there's 15, 50, 5, 10. Sometimes looking at the options can tell you whether you need to simplify. Now this case says we don't simplify. Be careful. Always guys, be aware. Awareness is better than, ignorance. Now, we know that the ratio of currents is going to be the reverse. It's going to be 10 is to 5 amperes, because the current is going to be 10 is to 5 amperes. Now, remember, our question is on the current. We're not interested in other things. So if the resistance divide like that, the currents reverse the ratio. Now we want I2. Now I2 is the one that is supposed to be greater than I3, because the resistance it's passing through is less. Therefore, current in the greatest amount will pass where there's there's least resistance. So we can say, well, I2 is going to take up how many portions? 10 portions of the current over how many portions? The combination of the two. That would be 15. Then we multiply by the total current, which is I1. Okay. So what do we see? This is option 10. Again, you don't bother with the rest. You just look at what you're doing. You get the clue whether you need to simplify that ratio or not, and then you answer the question. Makes life a lot easier. So understand the ratio and proportion things, how to use ratios and proportions. This is a skill you learn from way back, grade 9 to be exact. So it should not be too difficult to figure out what is cooking here. Now let's get to the last question and maybe take a small break and then continue. I don't know. But of course, you won't even notice that I took a break here. 1.5 in the circuit represented below. Circuit 1. The internal resistance of the cell is negligible, meaning it's insignificant. So the voltage available for the circuit is as good as the EMF of the battery. Now we're told your bulb A glows brighter. If it glows brighter, what does it mean? It gets the greatest current. Okay? And at the same time, it must be of a lower resistance than the other. Because for more current to pass, you must have less resistance. Then that means bulb B has a higher resistance, and therefore it will have the less current. Higher current, less resistance. Okay, but what do we know, guys? We know that V parallel is the same for the two resistors. Remember, when we want to look at certain things, we need to be very careful. We know that V parallel is the same for those two resistors. So they experience the same voltage. That's very important, because we can see they will each experience different currents, so to speak. So we can look at this and say this is power given by VI, which is IR times I. This is going to be I squared R. But the problem is that the resistance is less for the other one. The current is high, so this is not the best equation to look at for what is going on in here. So we can't represent this with the current, because we can see the current is not the same for the two, as well as the resistance is not the same. But we want something that includes a bit of a constant so that we can understand the difference between the two. So what would be the best way to split this? Again, we take the initial, this is the most basic power equation for electric circuits, but now we want to factor in the voltage. So we know that essentially power is V into, what is that? It's V over R. Because we want something that separates the two while they have some constant stuff in there. Remember, these are equations in a way, but these are graphs in a way. So this is V squared over R. Can you see? Now R is variable, whereas this dude at the top is constant. The dude at the top is a constant. Now, when we have a constant, we can actually picture what is going on. Because if we write this in the best way, we can actually write power as V squared into 1 over R. Because we want to study this relationship nicely and see what's cooking. Now, can you see, for us to decide which one has the biggest resistance, we will know it from here. Because we know that they each have the same voltage, so not a big deal. So this is constant. It won't change anything. But if R becomes less, what happens to power? It becomes bigger. And the bigger the power, the brighter is the glow of the bulb. So essentially, this is already suggesting that we have a low resistance because of this equation. So always, guys, work out an equation that will have a constant so that there's only two variables in that equation. And look at those variables so that you can understand what is cooking. Anyway, I cannot say more than that. So obviously this one, for the same voltage, to glow less, it means this one is greater, and then the power becomes less. Can you see? And that is the case. It has a higher resistance. So we can understand what is going on here. Even though the currents are also not the same, but they don't provide the best analysis of the relationships going on in there, because this is changing. It's not the same for the two. this is not the same for the two. So we cannot explore the relationship between R and P, for example, or I and P, when these are also not constant. There has to be a constant so that we can explore that relationship nicely. Now, we are told here that the bulbs are disconnected and then reconnected in series this time to the same cell, meaning same EMF, same voltage. Okay, this V parallel is as good as the battery, right? Yes, because there's no internal resistance there. Now, this is the same scenario, but now these ones are in series, meaning the current is going to come out and pass through both resistors. Okay, that's what we have. So, what would be the case? Now we can see that the resistance here is low, whereas the resistance here is high for the same current. So now what happens to the power? A different story now. Again, we go for power equals VI. Great. But now what do we see? What is the same here is the current. So we want to keep what is the same. So this means power is equal to, because the voltages are going to be different because of the difference in resistors. Remember, Ohm's laws tells us that V is IR. Now the different, they have the same current, is constant. If R is high, V is high. If R is low, V becomes low. Okay? So essentially, we know that the voltages are different for the same resistor. So we cannot express this in terms of the potential difference and resistance because these are not the same. We need something that's different. But now we need some consistency. So we can change V here into IR times I. So this means power is basically I squared times R. And what do we know? We know that essentially I is the same for the both. Now we know that the lesser the resistance, the lesser is the power. And the greater is the resistance, the greater will be the power. Same story. Okay? So this is what we understand. So this is the best equation to represent things in this circuit, so that we can understand what's going on, because it seems this thing is all about power, because the brightness is the power dissipated in that resistor. Now, which one of the following combinations represents the comparison of the resistance and power? Can you see? In circuit 2. Okay, now circuit 1 helps us to know that the resistance of A is less than the resistance of B. That's what it does. Then we look at the power now in circuit 2. What would happen? The power is going to be greater. So B is going to glow brighter than A. Okay? So that is the idea. So everything reverses in series. Nice. So what do we know? Resistance of A is less than resistance of B. Resistance of A is less than resistance of B. Definitely we were helped by circuit 1. So this is already wrong. So this already says this line is already forfeited no matter what. We're not interested. Yes, this may be right, but we don't care anymore. Now let's look at this power. We know that power of A is going to be less than power of B, because the lesser the resistance in this equation, because they experience the same current this time, the lesser the resistance, the lesser is the power. So if this is less, the power will be less. So this is good. So this is already our answer. It ticks both boxes. This is not true. This is true. This is not true. So we can see that the one that answers all the boxes is the answer. Okay, guys, so you can see I took a moment here to try and walk you through these questions nicely. Like I said, questions on MCQs have a tendency to have a strong bearing. Can you see we're dealing with vectors here? This means we're going to come across some question on vectors, resultant forces, and wada. We're going to have to deal with some objects hanging or what or combined. Something like this is going to come our way. Graphs and equations of motion are coming across us along the way. We will have to deal with all of these things. Trust me, these questions are an opening into the rest of the paper. So doing them first is the best thing you can ever do for yourself, because when you get stuck with one question, you'll still meet a question similar to it in the long questions. And that is going to actually remind you of certain things, because the structure of those questions might just be in a way that you can remember how to answer the question on the MCQs. And if you've answered some of the questions on the MCQs, it makes it easier to tackle those long questions. So you are most likely going to excel here if you do well on your MCQs. So this is something you guys need to work on, because MCQs are not easy. Those are already automatically higher grade questions if they're not direct. Direct questions are the only ones that are standard grade. And you can see here, even the direct question like this one, was put in a tricky way so that you don't understand it. It's easy, but not that easy. Even this one, I mean, it's one of the easier questions to answer, but it's not just as easy as it looks. So one has to be very, very, very careful. I mean, this one is one of those, Millikan's experiment stuff. Okay, again, it's one of those, because here we had to move from this equation and factor in this equation. So this means simultaneous equations. Now this is a concept we learn very well in mathematics, but you will forget when you get here that simultaneous equations actually apply. Because this is nothing but simultaneous equations working together, and then we explore the final result. How nice. And obviously your brain is picked here and there, and one has to really follow nicely and use every little tool. I think, guys, I am more elaborate for you. If you are really, really, really struggling, don't shy away to shout out. There's a comment section there. Pop your question. Verify some statements I make, because I don't even hear myself sometimes when I'm saying ridiculous things. I do say them sometimes. And sometimes I overly project to certain things that I should rather keep simple. But my intention is to be consistent in giving you as much as is necessary, so that as you study for yourself, you will also realize yourself what is not necessary. But at the same time, being aware of this over projection, because at times it is just what can take you across. All right, guys, so let us move on to the next question. All right, so let's hit question 2. We are told here that the instructions for this one, we start on a new page. We leave a line between, okay, this is section B actually. We leave a line between subsections. This is very important. Exactly depicted here that 2.1 and 2.2 must be separated by a line. And then we need to show the formulae as well as calculations, including substitutions. Can you see this common instruction is coming right here? And then number the answers exactly as the questions, because, for example, if it happens you answer a particular question elsewhere, if it carries the proper number 2.2, it will be marked correctly there. Okay. Now, let's see. Question 2 says, a rhino somewhere in Kruger National Park is stationary at point R. Okay, this rhino is here. Now, a game warden traveling at a velocity of 10 meters per second due west. What is that? Velocity, because there's magnitude and direction. Can you see? We dealt with vectors and vector components. Question 1. See, the very opening question of section 2 or section B is on the same idea. Okay. On an open track, fires a medicine dart. Okay. Horizontally from Q at a speed of 40 meters per second. See, this time they're talking about speed. But remember, horizontally from Q. If it is from Q, this means it's going away at 40 meters per second. So this is nothing but velocity as well. Sorry. Now we're told here the exact direction of this aim. The game warden aims northwards. So speed together with direction makes up a velocity. So northwards, so this means this is going this way, directly to the rhino. Okay. The effect of any wind or air resistance is negligible. So this is very important as a result of the distances and the speeds. So the close proximity here, we were not going to consider a friction or air resistance and things like that. Now that's key. Now we are literally just trying to create a closed system where everything acting is what we are given. Now this is the truck and it's traveling due west, so it's going in this direction at 10 meters per second. Then he fires a dart with medicine at 40 meters per second northwards towards a rhino there. Alright, so this is it. And then of course this is the compass again. See guys, unfortunately my stuff here is, is in trouble here. Some lines are missing. Some lines are just visible, so it's just a situation. Alright, so this is the compass. We know that north is at 0 degrees, guys, right? And then as we swing 90 degrees, this is east at 90 degrees, so we go clockwise. As we swing another 90 degrees further, this is at 180 degrees. We swing a further 90 degrees, this is at 270 degrees. And as we swing back to north, we complete a revolution. So this could be 360 degrees, or it could be 0. So it would depend on what is happening. So please, we use the bearing method, which is the clockwise direction on the compass, or north-south compass, sort of. Okay, please, that needs to be clear as well. Now, we're told here that the dart is fired directly towards the rhino, as we can see there. Draw a rough, see, rough, not an accurate. Accurate would mean we need to choose a scale. But now this one says rough, labeled vector diagram. So vector diagram, because now we're dealing with vectors here. Sometimes if it was forces, we could say force diagram, or you sometimes may want to say free body diagram or whatever. But this is a vector diagram which shows the resultant velocity of the dart relative to the ground that can be determined. Okay. So this is a very nice question. So let's start now. Question 2. Why bigger? Question 2. Now we have 2.1. We need to draw. Remember, from this point of shooting, we know that we will have ourselves that vector. Obviously, 40 meters per second is longer, so we always use this. We can say this is 40 meters per second in the northerly direction. But we saw that the truck was moving in this direction. Now this one has to be less than that. So this would be 10 meters per second in the westerly direction. So these are the vectors at play. And what would be the resultant? So we use the parallelogram method. So the parallelogram method, it means we just shift these vectors here. I mean, one can use the parallelogram method or the tail to head method. Right, so this would be giving us our resultant vector. So this would be the resultant velocity relative to the ground. Okay, so one can do this parallelogram method. It works. So this would be the resultant velocity. Okay, that would be it. Okay, all right, okay. But maybe let me do it better. It looks ugly like this. I like things that look a bit accurate. So we can have something like this. Let me do it this way. And then we know that this would be our resultant, that diagonal there. There has to be an arrow, right? So this is the resultant. And we know that this arrow is going in that direction. This is 10 meters per second. And this is how we fired this initially at 40 meters per second northwards. And that would be our resultant. Okay. So obviously the direction could be from north all the way. So this is northwest basically. But we don't really care at this point. We just draw what we are supposed to draw. But then when we're using the parallelogram method, we break this up because this is not necessarily there. So this is essentially what is necessary, guys. Showing the resultant here and showing those two other vectors amounts to 3 marks from this point of firing. One could consider this a free body diagram or whatever, but this is what it is. But somebody may choose to do a triangle and shift this force here and do the head to tail method, right? Head to tail method, okay? Or tail to head method. Sometimes it's very tricky to say what is what, but this is the tail to head method, okay? Well, this is from the tail to the head, so it sounds like tail to head method. So one could draw a triangle like this. So one could draw a triangle like this, and obviously we know that this angle is 90 degrees because these two are perpendicular to each other. So one could draw this parallelogram method of determining the resultant between two vectors, or one could use this triangle method, which is the head to tail, meaning we will shift this one there. Sorry. Or if you draw this one on this side, we shift this one up there. So it doesn't matter. So when we shift those vectors, that is an arrow over there. So this is what we would have, okay? So, but let's leave it with the parallelogram method at this point. But do note that one can actually use this triangle to answer the question, or even the other triangle, but then we'll have to shift this force up there, or we shift this force there. Nice and easy. 2.2 says, calculate the magnitude and direction of the resultant velocity of the dart relative to the ground. Remember, magnitude and direction. So very nice. Well, we've got options, okay? We've got options. We can look at this angle here. We can look at that angle right there and say this is angle theta. That can give us the direction if we choose this triangle. Can you see the triangle method or the tail to head method makes it a bit better because it helps us to use our sine rule. So sometimes it's nice to use that rather than the parallelogram method, but either way, you just do what you have to do. But remember this theta. Okay, let me show you how to do this first. So the triangle method becomes the best method at this point. Okay. So we know that this is the tail to head method. So this was 10 meters per second. This was 40 meters per second up, and this becomes the resultant. Okay, this becomes the resultant velocity. And we have to consider this angle theta now. But remember, this is north of west. So theta is north of west, but I'll show you the different ways to express this direction. Now, we can see that this is 90 degree. It's a 90-degree triangle. So what do? If we want the hypotenuse, we can use sine, right? Or even Pythagoras. We can use Pythagoras to get the resultant because we don't know theta. Then use the trig ratios to find the angle. So let's first find the magnitude. So we know that the resultant squared is going to be equal to 40 squared plus 10 squared. What do we know? We know some guy called Pythagoras, because that's a right angled triangle. This implies that r is going to be the square root of that sum. Therefore, r is, let's get the magnitude. So, got the square root of 40 squared plus 10 squared. Now with squares, now remember, nobody told us about the rounding off issue here. Nobody said anything about rounding off. Let's just double check. Remember, these instructions, guys, need to be clear. So nobody said anything about the issue of rounding off. So literally we can do whatever we want. So we can do whatever we want. So so what I'm getting here, this is 41 comma 23 meters per second. But now we need the direction. So we can just say, look, we can use 10 theta because we don't want to use what we calculated in case it's wrong. So we can say here, but 10 theta is going to be opposite, which is 40 over 10. Therefore, theta is going to be shift 10 of 4, basically. Let's see. Shift 10 of 4. That is 75, comma 96 degrees. Okay. Now what do we say? We can say therefore the resultant, because the question is on the resultant, is going to be equal to 41,23 meters per second. In which direction? We can say here 75,96 degrees north of west. Okay, one can put it that way. Another way to represent this means northwards 35, not 35 but 75,96 degrees from the west. Let me just check something quickly. Okay, so yeah, actually this is not correct. Now this notation says from the west, because we're from the west side. We're moving 75 degrees, 96, means 75,96 degrees to the north. Okay, so that's how we represent this using that notation. Or what can we do? We can just calculate. We know that this whole thing is 270, isn't it? So from the north, if we picture the north here, from the north, this whole thing, okay, this whole thing is 270 degrees. Then we add that, so we can just say 270. Let's just do it. Come on, say 270 plus the answer that we had. It gives us 300. We can just say 345,96 degrees. Okay, great. So these are the ways in which we can show the direction. So we choose any one of these three. It works out. But usually this is a question for grade 10s nowadays. I'm not sure if grade 11s get asked this question anymore. But anyway, guys, you know what is cooking, right? So you understand very well what is cooking here. So it's a very easy question, nothing really out of the ordinary, but some questions can be technical in this situation. So what do we get, guys? Well, we can do whatever we want, isn't it? So at the end of the day, we need 4 marks. So 4 marks is essentially any one of these two, any one of these three, actually. This 75,96 north of west, or from the west we move 75 degrees northwards, or we can just use our bearing and say that is already 270. We add theta to it, it becomes that. Any one of them, it's a mark, and the magnitude is a mark. Okay, so that's already 2 marks. sorry. Now essentially, guys, using a particular rule, that gives us a mark, isn't it? And also here using this rule gives us a mark. The rest was a means to an end. Okay, so I think this is how those 4 marks are scored. So if you're lucky to get a hold of this memo for this paper, it's good, because then you can see how many different approaches were used and how the mark allocations were used if this similar approach was used as well. Don't know why my throat is doing this thing now again. It's starting to irritate me. So let's do 2.3. 2.3 says determine either by an accurate construction. Remember what we did now was without construction, but we chose a rough sketch and we then used our calculations. Now this says either by construction, and here 1 centimeter should be 5 meters per second. So again, if a scale is chosen, you cannot choose your own. You follow the instruction, or by calculation. Now I'll only do it by calculation because I don't have a ruler here to show you this. Okay, include, if we're doing by calculation, what is the rule? We must include a rough labeled diagram. So this means you can't just do calculations from the air and expect us to know. You are taking maybe the sketch from there. The direction in which the dart should be fired. This time, it's a matter of what was the best way we should have done this, so that we end up on the rhino, because we can see that this way, the dart ends up where the rhino is not, because it is stationary, so we will miss the rhino this way. Because if we shoot it straight like this, but what is the resultant? It's over there, so we end up where we don't want this to be. So for us to get here, we then need to fire in a particular direction, usually in that direction, so that it will hit the rhino at point R. So this is a very good question. It's a typical higher grade question. Usually standard graders would not be asked a question of this nature. Maybe the first 2 could be, but usually for standard grade it's by scale drawing. Higher grade usually involves calculations. But I mean, these are easy questions. So guys, we can see that essentially for this to happen, this is the nature of how this should be. Right. Maybe let me do it better. We know there's 90 degrees here. And obviously, what we want the resultant to end up there, isn't it? So, wait, there's Anton go up. What am I doing? Remember, the resultant should be that one. Yeah, this is not right. My resultant should be at point R, so this is not the best sketch. It's ridiculous, isn't it? The ridiculousness, it means my sketch should be like this, rather. Yes, so that we still fire this one in that direction, whereas this one is going that way, and the resultant, it results in so hey, yanjija nansi into yewena ithi futhi uqela kabi nje go yewena. So if we're at this point and point R is directly over there, so it means we need to fire this in this direction, right? While this one is moving in that direction, right? So that the resultant is this one right here. So if we can just layer this here and say this goes like that. Is it a parallelogram? Maybe not exactly. Okay, it's not doing the things. Let me try again. Okay. Okay, so I tried because I want this one to be exactly vertical like this. Yes. So what we want, guys, is a situation like this where, remember, this is the original direction. So if we shift this vector, it comes up here. So this would be the 10 meter per second. And then this would be the 40 meter per second because we want to fire it in that direction. Whereas this one is traveling in that direction. And so that we have this situation like this. So that our resultant becomes this vector right here. Because we want to end up hitting point R over there. So this was from point Q. Okay. So now what we can do, we can take out the rest. So we don't want this one. So after shifting things, so you can use your ruler here to master this little thing here. So this is what we have, and there's 90 degrees between these two. So you can tell that it takes a bit of a moment to get the diagram right. So now it says we need to determine by accurate or by calculation the direction. So the question is on the direction in which the dart must be fired at that speed. So the direction is from the north, so we are looking for this angle. Now this is our theta. So that's what we want. So we know the hypotenuse, we know the opposite, we want the angle. So what are we going to do? See, this one is easy because obviously the first 3 marks is the sketch and representing those vectors with an arrow. So this one is worth 3 marks on its own. Now the second 3 marks is from the calculation. So we can say sine theta is going to be opposite 10 over 40. This implies that our theta is going to be arcsine of 1/4. Right. Therefore, theta, remember now this is just using the bearing method, so it will give us the exact direction. So we can leave it as just those degrees. We measure them clockwise. So shift sine of 1/4 or 1/4. So this one is 14,48 degrees. Okay, so this is already good. Now answer the question. There was no theta there. We can say therefore the dot should fired at 14,48 degrees to hit the rhino. Okay, that's it, because the question was on the angle. The speed is this, should be fired at, maybe let's even mention that speed, because hey, we can't afford to. Should be fired at 40 degrees, 40 meters per second, 14 degrees. Ikhona into nje at I ask siyibhale bafethu, what can we do at abaninzi at 40 meters per second at an angle, maybe we can say at an angle of 14,48 degrees to hit the rhino. Now this is the answer. So always try to answer the question, because we introduced our own things. I cannot show you guys the scale drawing, but the scale drawing, you'll just do the same structure. But what you will then do, you'll use your protractor to measure theta from the north to south. It would come out more or less the same. Maybe you could get 14,5 rounded off to the single decimal digit. So that should be okay. All right. Again, second thing here is defining the trig ratio in question, and essentially whatever gymnastics you had to perform and answering the question, okay, fully. So that is just how this goes, guys. So you can see that this 6 marks was just a gift from the examiners. Usually question on vectors is not that difficult, as long as you understand what is going on and how to structure it properly. You'll probably get your answers just right. Okay guys, so this is essentially how easy these 13 marks could be scored, okay? Nothing really big. Can you see? Just 3 marks. 3 marks. The first question was really not a very difficult question. And remember, this is a triangle. Literally, we have 90 degrees. Opposite 90, we've got 40. Theta, opposite it, we've got 10. So we can even use the sine rule. So use the sine rule. Okay? And at the same time, one can also use the cosine rule. Right? Because we already know the value of the resultant force. We know that it has to be 41,23 meters per second. So this is it right here. This is still 41,23 meters per second, because it's still the same resultant force. So we can use the cosine rule and say this is theta, the included angle, the opposite side, and all that. So the triangle rules can actually be used. So remember that. Pythagoras is not the only one. So the triangle rules can be put to good use. in solving the problem. So however you see this, so try using them and see if you're going to get the same answers. All right, let's move on to question 3. Now, let's start this on a new page by following instructions. Now, question 3 says, a crane in East London Harbour lifts a crate. This could be what we call a container. I mean, if we're using a crane, this could be a container. Those big heavy things. Okay, of mass 300 kilograms. As you can see, it's quite heavy. From the deck of a ship. Okay, it then moves the crate horizontally. Okay, not a big deal. Above the surface of the water and stops. Okay, now we can see something like this and say, okay, there's our ship right there on the water. And of course, maybe this is the house of that ship and all that. And then there are the goods. So this is the container that we're trying to remove. And there's the crane with whatever is making it work. So this crane is usually very long, right? And then it's going to pick up this crate, move it horizontally so that we end up with this crane maybe facing in this direction like that, and then there's the house, and then we've got our crate there. So it moved it horizontally off the deck above the surface of the water. Okay, so there's our crate now, or container. Set it like that. And then it says the crate is now lifted vertically upwards. Now lifted vertically upwards. So this means now the crane starts moving itself upwards. Okay, it's climbing, or maybe it's pulling on this rope, but so that we have our crate going upward like that. Okay, now at a constant speed. This is very important. If this is happening at a constant speed, what does that mean? Acceleration is 0. Okay, it's doing this at acceleration that is equal to 0, meaning the resultant force is 0. Nice. Okay, so now if we draw a free body diagram of what is going on the crate when it is lifted vertically upwards, we can understand that the force of the crane is equal to the force of gravity on the crate. Okay, so that the forces are balanced. So this is essentially the statement being projected. Now I told you when the crate is 30 meters above the ground, above the water, while it is still moving upwards, see, the cable holding the crate snaps. Now remember, if this thing has velocity, it has momentum. So that means when it cracks, it will still continue upward. So we end up with a situation where we have now the surface of the water here, and then we've got the crate over here. The crate will still be moving upward, reach maximum height, and then be on its direction downward. We don't know, but we know that this happened when the crate is at 30 meters above the ground. So can you see the main question starts when we lift this vertically upwards, because the rest of the other story is just offloading the ship, so it doesn't really help us much. But the main question, because this is vertical projectile motion, starts here. So sometimes you get given a lot of information that you need to process and be able to organize and answer the questions appropriately. So we end up with this situation because now we know that there's this initial velocity, which is this constant velocity, which we don't know, but we know that it is some value x, right? It's not negative because it's going to move up, but at maximum height, we know that the final velocity is 0, right? and then it's going to move down. Let's read on. The cable holding the crate snaps. Now the velocity time graph. Okay, again, we're still dealing with the velocity versus time graph. Do you see one of those MCQ questions on velocity time graph? Let me just take you back to refresh your memory. Look at this one. Something was given initial velocity, it went to maximum height and then came down. Nice. Similar question. So if you couldn't see it there, now this one walks out the window. But if you saw that one, an added mark here also to pick up. Okay, sorry. Velocity versus time graph below represents the motion of the crate from the moment the cable snaps, okay, until it hits the water. So this means this will progress to go and splash on the water. Maybe the crate will sink, we don't know. Okay, but all we know is that there's going to be a huge splash of water. Okay, now downward motion is taken as positive. Can you see? Sometimes you are given a chance to choose. This time these guys are choosing. And the effects of air resistance. Now this is the statement we've been waiting for, because we could picture a projectile. But now if we can ignore air resistance, this means the only force acting is gravitational force. And therefore the crate here becomes a projectile. And what is a projectile again? It's an object that is given initial velocity and subsequently undergoes motion that is influenced by the gravitational force only. And if this is a projectile, it means the acceleration is g, and g is always downward. Now in a velocity time graph, g is the gradient. The gradient, can you see it's constant and it's a positive slope because we chose downward as positive. Unfortunately, this one dictated the direction. So be very careful to understand the diagram fully so that as you answer the questions, you are answering appropriately. Now we can see this is the initial velocity. Remember, we used the letter U to denote the initial velocity, and we used the letter V to denote the final velocity. And this is nice and clean, unlike this VI, VF. It's ridiculous, is it not? Yes, go and tell your teachers to influence a change back to the right thing. We need clean things, not complicated things. Anyway, whatever they choose, in fact, they don't have the power, so whatever. Because they have to suck up to some other form of influence. They don't influence themselves. Ndiyayazi loo nto leyo, noba ndingathini nandaba nayo futhi loo nto leyo. If uyanikhathaza ndiyaxolisa, kodwa andixolisi. Listen to this arrogant freak. Whatever, man. Now what is going on here? So this is at maximum height. Do you see? From the time of launch, it reached maximum height after 2 seconds, because this is time in seconds. So this is the time from the snap to maximum height. It took 2 seconds because the maximum height is at 0 velocity, like we know. Then the direction changes because then it moves down. Now as it moves down, this is positive, and now this is the velocity when it hits the ground, hits the water. So that would be the velocity when it hits the water, because we're told it does hit the water. Okay, so we can really read this, but now we don't know the time right there. It's not given to us, so that's a potential question. But at this point, we understand things. Even this velocity, it's a potential question. But we know the gradient here is 10, it's 9,8 because it is g. G is 9,8 meters per second squared. Nice and easy. So we understand our diagram. Now we are ready to answer the questions. It says, what does the gradient, what does the gradient of this velocity time graph represent? Can you see? Having revised our knowledge, I'm going to do this, guys, just to annoy you, to show you that all these things are connected. Do you see we made a revision here? And can you see how this now comes out nicely? Those questions, if you mastered them and did a bit of a background check, can you see now this becomes a nice one? So it says, what does the gradient of this velocity time graph represent? Now let's answer. 3.1. It represents what? Gravitational acceleration. You can say G. That's 2 marks on its own. It says state also, without doing any calculations, the magnitude of the gradient. And the gradient, we know that this is basically 9.8 meters per second squared. Okay, the question was on magnitude, so we don't need to show the direction that it is downward. But because it's a vector, this thing. If you put it in brackets, it's not going to affect your answer. Even if it's wrong, they're not going to mark it. Okay, but if you don't put it in brackets, you're automatically forcing them to mark it. And then if it is wrong, it messes up everything. It means you copied, you didn't write this by yourself. So sometimes refrain from getting extra information in when you show it's not working, or have a way of putting it. But when you're putting it in brackets, you're saying it's not really significant. That's the essence of this notation. I don't know if it still applies today or not, but back in the days, it kind of protected us. If you put it in brackets, if it's wrong, then they would not consider it. You get a mark. But if you don't put these brackets in, it means you are confident. Because this was a way of saying, I'm not too sure, right? But if you are saying, I'm very sure this is, then it means, this one, then it goes wrong. But let's say this was correct and it was necessary. Then you are saying, I'm not too sure, but I'm giving an aim. So that's something. It's like guessing. That means it's an attempt at answering the question. So do you see the psychology? That's why teachers need to understand psychology. They need to go through psychological training so that they can understand the mind of their students. Again, there's some standards that have been created to kind of, send this message clearly. I don't know if this still applies. So please don't do it if the teachers tell you not to do it. But these are some of the things that we understood to save us from the devil. The devil being the examiners. And our saviors being the markers. Because the markers have to understand us so that they can save us, isn't it? Yeah. Anyway, anyhow. So can you see, guys, an extra mark? Easy 3 marks. Of course, this is a gift from the examiners. This should be 2 marks, 1 mark each. But the examiners are just trying to say, if you understood this picture enough, that we are dealing with the projectile motion here. And therefore, the acceleration is gravitational acceleration, and therefore that's that. It means, can you see that revision? It looked unnecessary because the question was more or less straightforward. But now it comes in to our rescue in this question. So please, guys, don't ignore certain steps that need to be taken. Now it says determine the constant speed u with which the crate was being lifted before the cable snapped. So we want the initial velocity. Again, guys, if you look at this, this is more like this hot air balloon type of question, because this one is just trying to create a different flavor of this hot air balloon situation. Something is moving it up and then it snaps, but it will still launch at the same initial velocity, which will then decrease because of acceleration due to gravity now alone, and goes to 0 and stuff. So we can work this out. Now, nobody said how we're going to do this. Sometimes you get a situation where somebody says without using equations of motion. Then you're like, oh my God, what am I going to do? Sometimes you can do whatever. So if you look at this triangle is informative. One can use this triangle to deal with this because we know the gradient. We know the x. We can determine the y using the gradient. Just the gradient, because here nobody told us what to use. Or if we like, we can use equations of motion because we want initial velocity and we know all of them. So we've got the time to maximum height, and we don't care about the final velocity because, wait, do we not care? It's 4 marks. This could involve 2 steps. It could be 1 step. It depends on how one looks at it. Let's just look at it in terms of the gradient in this section of this triangle. So we can say here from, or maybe we can say for, maybe let's just say motion. Let's just be complete. We can say motion for the first 0.2 seconds. Now, always be clear to the examiner what you are doing, especially the one who's marking, because the examiner is not there to see what you did. But the marking person is going to now figure out what is the student getting at. So when you elaborate, you're already easing their pain of not getting you right. Sometimes it happens that the memorandum is wrong in approach, or perhaps it did not accommodate your method of solving the problem. But if you elaborate, then the examiner understands exactly what you're doing. So they may not struggle to mark you correctly. Because if your answer is correct and it is clear and everything is legal, you get full marks even if nobody cares about these short areas of getting marks. As long as you are clear where the formula has been applied, the substitutions and the approach, okay? And the answer is presented correctly. But if you don't do that, then you lose marks because no one knows how to mark you. But again, this can be sent for review by the examiner. Is this correct? Okay, how do we mark this situation? Then they can decide, because they decide where the marks go anyway, especially when you don't get the answer right. But if your answer is correct, automatically get full marks, if of course everything is coherent. Now motion for the first 2 seconds, we can say the gradient is equal to 9.8. We know. But of course, get Tina, guys, we were using 10. So there may be a problem here. G for us was 10 meters per second squared. I don't know why they changed even. Because what's the point of introducing decimals? I mean, guys, come on. They like to complicate unnecessarily. But anyway, whatever. Now, usually this paper was under the notion that G, again, be careful, look at that information sheet for, during that reading time, look at the symbols, because you may find that in this next exam, without a warning, because instructions are saying read the paper and see everything, they may decide this coming exam to write G like this, but not warn you. When uqhubeka ubhalo 9.8 because mazi kwi-textbook senjalo nakweza exam guidelines. Like I said, the guidelines are mere suggestions. They are not rules. So they can be bent in a given paper to test a student for accuracy in following instructions. And someone is going to cry and say, but this is unfair. We know Tinbang 9.8, 9.8 in your head. Did you look at this specific paper and see what was the specific dictation or the specification? So again, the formula sheet is good to look at before you even start answering, so that you can see especially things like these constants that are involved. Look at them because they can modify them. Remember, it does not necessarily have to be what it is in reality or how we accept it. This is an exam. We can do whatever we want to test our students, because at first we want to test awareness. Our students are aware that most of the time when they have a problem, the solutions are in and around that problem. This is another way of checking. Let's say we change this constant slightly. Yes, you know what's the right one, but we write it wrong. Don't cry and say this is wrong. This is deliberate by the examiner to check if you are going to follow instructions. Sometimes they don't give you a lot. So with higher grade, it was never really about what you know is the standard. It was all about what does this paper say. Okay, so apha ithi ngu-10 ke guys. So ndifuna unifundisa ukulandela instructions, not just what you know. Sometimes follow the instructions at hand. That information sheet would not list it if it is not going to be used like that. There are certain, things that, you look at, and some things you don't. So the gradient is equal to 10 because it represents G. Okay, great. But now how do we determine a gradient between 2 points? We know that this is 0.2 minus 0. I mean, I mean, we say change in y over change in x first. So this is going to be u minus 0 over 0, 2 minus 0 as well equals 10 over 1. Right. Now this simply means this is just u over 0, 2 equals 10 over 1. We just cross multiply that to sort out u. We can say therefore u is equal to, okay, all right, okay. Now the thing is u is negative here, but here it's gonna come out positive. But either way, we will find a way of adjusting this, because some calculations are not necessarily going to give you the right answer in its right format. You will have to account for it, because the question said the constant speed. Now, speed is a scalar quantity. It has no direction. So we don't even care. The answer should be positive anyway. So this is going to be 10 times 0, 2. Let's do that nicely. So this is 10 into 0, 2. That gives us 2. So this is 2 meters per second. And of course, we know that the question said speed, so we don't need to worry about direction, because speed in its nature is a scalar quantity, so we don't consider this. Okay, guys, so this is great, because this is like some sort of a formula, okay? And then the correct substitutions into that particular formula, okay? Nice enough, and then we get an answer nicely. This would be 3 marks, because I mean it's a plug and go type of a thing. But one could easily say for the left hand side, because that left hand side, it's some kind of a calculation of some sort. We can award an extra mark for that. So with higher grade marks, did not necessarily mean too much work, but it meant some skilled work, if you think about it. So that was just the difference between your curriculum. Yours is mostly standard grade, and to some extent some higher grade. As a result, you can predict everything there. But with these higher grade questions, you will also notice in some of your exams, the higher order questions, they have a tendency to have less marks, but a lot of work in a question to try and protect you from losing the mark. Again, to also fool you into thinking it's a simple question when it is actually hard. But here you knew with higher grade, you never knew what to expect. You just had to know it all. That most likely more steps, but less likely could just be a single step, and that's it, as you can see here. Nice, guys. So we can go about it this way. We get our 2 marks. I mean our 4 marks. Now let's use equations of motion, because no one said how. A determination, it can be by any means necessary. Because guys, this is now a practice for the finals. We're not really chasing time. We are chasing knowledge here. Now we can use something. We know the final velocity is 0. Initial velocity we don't know. The time it took to get there is 0, 2 seconds. And essentially the gradient is the acceleration, which is 10. So we can use the equations of motion that essentially final velocity is equal to initial velocity. I'm going to use this context now. Plus gt. So we didn't use these delta things, as much as we knew that was a change in time, but come on, man. Why must we suffer? We don't need to. So this is 0. This is 0 into u plus. Now remember, we chose downward as positive. Be very careful. So this is now 10, which is positive. The time is a scalar quantity, it's 0, 2. Can you see? Therefore, we see that u is going to be minus 2 meters per second. Because this one, remember, equations of motion are based on vectors. We're defining vectors here, not scalars. Because you will see that in all these equations of motion, let me just keep doing this, guys, as annoying as it looks. If you look at equations of motion, they are defining vectors. Velocity is a vector. Displacement is a vector. So all of them are defining vectors. As a result, we tend to have answers that would be vector-like. But knowing the question at hand, we can adjust the answer accordingly. So obviously we can say therefore the initial velocity here is going to be 2 meters per second upwards. Because we're just trying to account for this negative, because remember they said the speed, so the speed must be positive. So do not present that answer as negative, as much as on the graph it is u, but we need to be very careful. Upward is positive, and if we're saying speed, we are saying scalar quantity, not vector quantity. So can you see, guys, same thing could be answered any other way. Formula, substitutions, and knowing the value of g, and the answer with its correct unit of measurement. What is key here is the correct unit of measurement. If that is missing, 1 mark gets lost. Can you see, this is normally a 3-mark question, but as you can see, because of some skilled knowledge, that this is 10, because nobody spoke about it, nobody said this is a projectile. You had to understand from the statement itself. Well, the examiners felt, let's gift, because this is a gift. Honestly, a student has to know that. It's not even a question, it's a must. Okay, so this is how one could look at this. Okay, so guys, I don't want to complicate this matter any further, so this would work nicely. And of course the other person could use this formula, S equals ut plus half gt squared, because this could work as well. But the problem is that you don't know the displacement. That's another issue. So in fact you can't, because you'll have two unknowns. You will have this as an unknown and that as an unknown, so this is not going to work. But you know that technically you can use it, because a brave student will say, but even if I don't know it, I know that this is the area of that triangular part, because for the first 2 seconds, 0.2 seconds, you can actually calculate that area in terms of u, because there's only going to be u that I don't know, but everything else I know. Right, let me show you, so that at least we are complete here. So I'm trying to show you that instead of doing this separately, now this is essentially using simultaneous equations, because you can see this is not completely solved, but because it will present just one unknown, we can go about it nicely. Right, because now this is a triangle, so this is going to be half. The base is that time, which is 0.2. The perpendicular height would be our u. This is equal to ut. Now the time here is 0.2 plus half ug wethu ngu-10, ixesha lethu ngu-0.2 squared. Can you see? Simultaneous equations, but now just doing it in one step, because I don't have time to waste here. So all I have is 0.5 into 0.2. That becomes 0.1. So I've got 0.1 u equals 0.2 u plus, we saw that, okay, let's sort this one nicely and not cause problems. So we've got 0.5 into 10 into 0.2 squared. So this gives us 0.2. Nice. Can you see? Now these are like terms. So what we can do, we can transpose the 0.2 to the other side and then do this. 0.2 minus 0.1 gives us 0.1 u equals essentially minus 0.2, because we transpose this to the other side. And therefore we sorted out u is going to be equal to minus, now we say that one divided by 0.1, it gives us 2 meters per second. And of course we can present that this is 2 meters per second upwards, because this is now a vector, so to speak. In fact, you can even ignore the negative, but remember your answer must be presented according to the question speed. They didn't say the velocity. Even though the graph, you would see that u is essentially a velocity there, but if the question says speed, answer according to the question at hand. So you can see that yes, it looks like a dangerous water to swim in because there are sharks here to catch you. But if you know how to deal with sharks, you can swim with them nicely. You'll still get the same answer. But be very smart at using simultaneous equations. They can hurt if you're not careful. Sometimes choose the simplest approach because it solves the pain nicely. So as you can see, guys, we get a mark for our formula. This is a calculation on its own. It warrants a mark. This is a calculation on its own. It warrants a mark. And then we get our answers nicely. So 4 marks still achieved, but more work. But who cares? We know that a 4-mark question can be 2 steps. This could be a single step, deriving an equation, and then later substituting one into the other and solving. Either way, you still get to the same answer. However you get to it, please get to it. Sembelieve torho ndiyakucela ndiyakubongoza mntwana wesikolo. Unganicaphukisi ngokuba ligwala or giving up. Okay? Mawubonakalisa ulikroti, uligorha, ulitshantliziyo, ikhalipha. Sidibananga namagwala thina. Science ayiwafuni ke futhi. Usuke nje kuyibuligwala. Okay, all right, okay. If you didn't get that one, just simply says this is the home of the brave, guys. You know, the valiant or valiant. Is it valiant or valiant? It's valiant. Amakhalipha kwetini. Into ezingoyiki into. Yes, 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 and yes. All right, determine by using the graph. See, this time there's a dictation on how we're going to do this. Okay, so can you see here we combined using the graph and equations of motion in a smart way because there was no dictation as to how we do it. But this one says determine by using the graph, not any of the equations of motion. So if you find yourself using equations of motion, you are dead. Okay, ungofileyo. Now the maximum height which the crate reaches above the position where the cable snapped. So this is not the maximum height above the water, but it's just that portion. From the moment this cable snapped, this is the height we are looking for. And what do we know? Height is a scalar quantity. So we will ignore a negative answer, although upward would be negative. So if we get a negative answer, we're not going to care because all we care about is this one. Because now our u is -2. Okay, guys, so I heard as if there was something cracking, so I wanted to make sure there are no issues there. Okay, now so let's do the question, guys. We have to use the graph only, and we can see it is going to be this area under the graph, the very same area we just used. Now we just simply plug and go. Again, the extra mark is just adhering to the instruction. You get a bonus mark because this is a 3-mark question and it's one single step. So we can say here height is going to be equal to, remember these sketches are there, you can even annotate them. Height is going to be equal to the area under graph for first 0.2 seconds. Please, guys, be very clear. This is equal to. This implies that our height h is going to be equal to. Now this is a triangle, so it's going to be half base times height. Now we continue. This implies that our h is going to be equal to half. The base is the times 0.2. The height is now going to be that 2 seconds. So here we just substituted positively. There's no need to put a negative there. It's not a big deal. Therefore, the height is going to be, maybe we can say h max But I don't want to use that word, because the actual maximum height is that whole height. Maybe let's not do that. Now let's finally find the value. So, I mean, this is just 0.2 meters, isn't it? Because 2 and 2 will take each other out. So we get 0.2 meters. Remember, the height is in meters and it's a scalar quantity. We ignore the sign, if ever you substituted the sign. Okay. Because sometimes somebody asks correct substitutions, they have to speak sense in terms of the graph because we are using the graph. I don't know if there's a need for this. And then we can just put another argument here and say h is going to be minus 0.2 meters. But because we understand that this is a scalar quantity, we then ignore the sign. I'm not sure. But obviously, guys, when we're told to use the graph, I think it's appropriate to indicate the sign, because on the graph, the sign should be negative. I suppose this is where also the catch could be if you don't substitute correctly. But I don't know how much of that would actually impact. So higher grade was all about being meticulous. Sometimes a simple question could easily be a nightmare, in that if you don't listen to the instructions, remember, use the graph. According to the graph, u is negative. So if you show up with a positive, it means you did not use the graph. You used your own thing. Okay. Hey, there was a big problem. So again, guys, stating the fact. Can you see that revision we did when we were answering the MCQ? It's coming to effect right now. You get me? So we're getting a substitution into the formula. We're getting an answer, 3 marks. And where's the extra mark? Obviously, guys, even though we know this is the area under the graph, we still need to show a formula of some sort. Okay, that is non-negotiable. So again, I mean, if you look at the extra mark technically, it's just to say adhering to the rule, essentially, more than just knowing what it is. Nice and easy. Nice and easy. Now must go again, guys. Say pendulum, and of course there's no other way. Remember, we were restricted in how we solved this one. 3.4 says, show without using the time of fall that the magnitude of velocity v with which the crate strikes the water after the cable snapped is this one. So can you see here the examiner is being friendly, because they could not even show you that answer so that you just do it. If you get it wrong, you get it wrong. At least you're being told you that whatever you do, this is the answer. But can you see it's just 3 marks? This is to suggest this is a single step. There's no point in suffering here. So here, no one said without using the equations of motion, but we must not use the time. Meaning we can't, because in any case we don't know what that time is. So it would not be possible anyway. So let's have a look, guys. So what do we know now? We know that we can use this equation. S is equal to ut. It has time. We can't use this one. So which one doesn't use time is this one. V squared equals u squared plus 2as. Obviously, guys, your equivalent is Vf squared equals Vi squared plus 2g. In fact, I could use g here. There's no a here. There's g. Now g delta y, because this is vertical. So this is the best modification in your current syllabus, okay? But now I'm being specific to this paper because I'm trying to teach you something. Look at the instructions given. If it says follow instructions, remember everything in this paper applies in this paper. So you look at those constants, you look at that thing. But of course, there are some areas of flexibility, like in this case. You can do your own thing as long as it is correct and you are clear as to what it represents. That's not a big deal. But don't be too, don't be too, don't do. V squared equals, now we can use the initial velocity. This was minus 2, we got it, squared plus 2 into 10. And this displacement, we know now that the maximum displacement. Now here's the trick again, guys. Here's the trick again. You will be in trouble if you don't master this nicely. Do you see from this point, how is this box being displaced eventually? It's actually being displaced downwards like that. Isn't it? Because even though it goes up, it comes down to the same position. So that cancels itself out. But what remains is this, from the starting point to the end point, we're actually displacing it down those 30 meters. That is the key. It's easy to not know what to substitute for the displacement here, because one would want to consider the addition of those two. Now that's a different formula. I will show you also how to use that, just in case you chose that route. So this implies that our V is going to be the square root of this whole shenanigan. Remember, this already told us that we're choosing down as positive. So that's why these are positively substituted, because G is downward, the displacement is downward. So the initial velocity was that. So when you say correct substitutions, we mean even accounting for the signs. Now, let's do it. Let's do it. Square root of minus 2 squared. Okay, plus 2 into 10 into 30. Into 30. Good 30. 2 root 151. And guess what? Indeed, this is going to be 24, comma 58 to 2 decimal places meters per second. Remember, the question said magnitude. So if it states magnitude, we don't care about the direction. But the good thing is that with the square root, it's plus or minus. But we can see this is already positive. So we leave it as such. We don't stress ourselves anymore. So obviously, guys, for formula, and then substituting this correctly, that's a mark on its own. In fact, let's just say correct substitutions and the final answer. But sometimes the final answer is already volunteered. I would say this mark is weak here. But what is strong? Already 10, we knew it's positive, but this 30 is a significant substitution. It takes courage to note that. So those 3 marks are effectively there, rather than the final answer. But it has to come out for you to get full marks. And it has to come out from this calculation. Everything must be coherent. Okay. Easy stuff, isn't it? Yes, guys, very easy. Or one could look at this entire motion from the very top until down there. And say from the very maximum height down there, we can still use that. So we can use the same equation. V squared equals VI squared. Okay. 1 says dozin. Says weighs in. Let's try to be particular to the question. 2G S. So this is going to be V squared equals the initial velocity, still the same thing. But now remember, the initial velocity becomes that final velocity there. It's not the same thing. Yeah, it was about caught out, pants down. This is downward, and 0 doesn't have a direction. Now what is the displacement here? It's going to be 30 plus that 0,2 we calculated. Now this implies that our V is going to be the square root. Always, guys, simplify things systematically. Trust me. Jumping for the jugular here might hurt. This is 30,2. Don't jump for the jugular premature. What prematurely? do not do it. So this is 30,2 there. So we just modify the other one. Can you see? If that one is not, you get the same answer. It's the same answer. So this is 24,58 meters per second. And we can see on the graph it's positive, so it's good. The question was on the magnitude. It was not on the direction, so we don't need to specify that. So again, you get a mark for the formula. This is a calculation on its own, and the entire substitutions. That is what gives us the marks there. This whole calculation is just answering the same thing that has already been given. So can you see, guys? There are many ways of killing a cat. By all means, kill that cat. And of course, guys, you will get this memorandum in the description together with this question paper for future reference. So you can check on the description of this video. You will find this there. Of course, I may not put it immediately, but I will be able to provide it there. So you can check a day or two later. That should be there. Okay, guys. Now I'm just moving too slowly over very simple questions. You understand? Yeah, man. So let's do 3.5. Now 3.5 says, the crate of height 2 meters. Is it necessary? Asas. So this means this is 2 meters. But be very careful when information is given. The most important thing is to know what is what, because it says now, which is completely sealed so that no water can seep in, penetrates or sinks the water to a maximum depth of 1,5. Now what do you understand, guys, by the word maximum depth? Remember, we talk about maximum height when you're going up. Maximum depth means turning point. So this means here at that turning point the velocity is 0. At this depth the velocity is 0, because remember, this first part of the thingy will essentially hit the water at this velocity, then it drops to 0. Okay, so at the beginning we had 24,58. Now that would be the initial velocity essentially, because this is at the top of the water. Then this is the portion that sinks, 1,5 meters. And then the final velocity, which is maximum depth, is basically going to be 0. Meaning it will stop momentarily, then probably going to be pushed up, or it will remain suspended in this manner. We don't know. Before rising again, or it rises. So that means this thing is going to be pushed back to the surface of the water. So at the end of the day, we'll end up with the surface of the water like that, with our tank sitting like this, or crate. So this means the force of the water is greater at this point than the gravitational force. So it doesn't get suspended like that. So it gets pushed up there until the water and gravitational force are balanced. Okay, nice. This is interesting. So at this depth, we know that the force of the water, which would be the normal force, is going to be greater than the gravitational force, which is Fg. This is at that depth. But once we reach here, we will see that essentially the force of the water, which would be the normal force this time, is equal to the gravitational force. Okay, guys, think about these things nicely, because if you do not make an effort, these questions can be a nightmare. Obviously, guys, we're just spending some time with these questions and enjoying. I could easily answer these in no time at all. But what's the point of showing my charisma instead of teaching you something? You see? Now draw a labeled force diagram. Obviously, we'll cry about your data, but I'm not interested in that. If you want to learn, you need to sacrifice something. If you don't want to learn, move along. Go and find the speedy ones who are good still. Maybe you learn fast. It's fine. But I'm accommodating any form of student. But You will be annoyed, of course, if you're a fast student. You will be enthralled. Is it enthralled? Or you will be thrilled if you are a slow student, because this pace is good for slow students. But it is not bad for fast students, because remember, for you to be even better at your speed, you need to take it slowly first. Then you can see where the traps are, where the danger is, and then you make up for it. Then you can go about it fast. So this pace accommodates everyone. But if your temperament is too fast for this, you are in a wrong place. Please run away. It's advisable, you see. Now, draw a labeled force diagram, see, of the vertical forces acting on the crate when it is at its lowest point, or the maximum depth. Now, the length of the respective vectors should indicate their relative magnitudes. Can you see? This one is a very packed question, so very easy, but it's packed. Again, 3 marks. This is effectively 2 marks, but the catch is on something. So we know that we have this force and that force. Remember, at the depth, they are not equal. So we've got the force of water on crate. Of course, someone can say normal force. That would be understood. It's still true. And then this one is the force of gravity, Fg. Okay, there's no need to write this in full, obviously, guys. But can you see the magnitude? But again, my sketch is not quite straight, guys. This is dangerous because these are vertical forces. When we say vertical, we mean vertical. So this nonsense of saying something that is a bit squiggly is vertical, it's ridiculous. I can go. Senza uqaphuka ke. Yewena. Yo, Nkosi na fefa wathi siyimuve kancane. Thengade ufuna umqhela. Ayi. Ifuna uba slanted, guys. Masiyeke ifuna unihlanyisa. Dingekahlanye njalo masese siyeka khona lapho. Okay, remember this set force diagram. So here we can put our friend. This is our friend, the crate. Remember, this thing has to be labeled. That's the crate. That's everything, everything. So what is important, guys, is the names of these forces. Of course, normal force is acceptable, or you can write force of the water on crate. Fg is acceptable, but you can write gravitational force if you like. It's up to you. And indicating that this is the crate is also good. Okay. So the third mark is for everything, showing those lengths, that they are different. That's the extra mark. So as you can see, higher grade was not really like standard grade. The number of marks does not necessarily correlate to the number of forces in question, but it's all about the specifications. If you adhere to those specifications, you get the extra mark. If you do not, you get sucked into the swile. Okay, folks, nice and easy. So 3.6. Now we start to get hit with something interesting. Determine the average acceleration of the crate from the moment it strikes the water until it reaches maximum depth. Okay, so this means a deceleration, to be honest. Now, this is a nice question because we know that this will stop, so it will decelerate. But now, what displacement did it take? Remember, this part moved from there to there. So this is the displacement this crate moved. Its total height does not matter because it did not sink completely. You see? It did not sink. Wait. Let's wait. Did it sink first and then it submerged like this? Completely sealed so that no water can seep in. Penetrates, sinks into the water to a maximum depth of 1,5 meters. It is itself 2 meters, meaning it does not go in completely. So the part that goes in is this one. Okay, so that means we can ignore that 2 meters. It's just there to confuse us. Because what moved is this edge. It dipped down this much to get that 0, and then it moved back up. So this means this is the displacement. So we've got initial velocity, we've got final velocity, we've got displacement. We can actually find the acceleration using our equations of motion, because nobody said we can't use that. So we know that final velocity equals initial velocity plus 2. Now this time it's A, because it's no longer G, because there's not just gravity acting. Remember, this is the situation. So there's another force acting with gravity, so we can't write G. But the displacement, we have it. I forgot the squares, sorry. So this means, what is the final velocity? 0. A very important realization, otherwise you would be caught out pants down. At this point, remember, everything was taken such that up is positive, so down is negative. So our initial velocity is going to be minus 24,58. Remember, there's no need to worry about rounding off. It is already rounded off. We put it as it is. Plus 2 into A, which is what we want, into S. Remember, this is downward. Downward was taken as positive, so this is 1,5. Holy cannoli. Konje besifuna ntoni A, okay. This implies that if we isolate A is going to be 0 squared minus into minus 24,58 squared, all of that divided by 2 into 1,5. Now I like to do this portion of this stuff so that I can just punch easily onto the calculator without mistakes. So fraction button, 0 squared minus, I punch it as I have written it, minus 24,58 all squared divided by 2 into 1,5, which is nothing but 3. Now what do I get, guys? I get a minus 201,39 meters per second squared. But the question said the average acceleration, didn't say magnitude. So what do? We can then write this as 201,39 meters per second squared upwards. This direction is necessary this time around because this is a vector quantity. We need to interpret that negative as much as the direction dictates so by the choices made, but we need to show that we understand that, because we can't present a negative answer. We have to interpret the negative quality of that answer. Now, do you see, this is where these marks come from. It's not about anything. Obviously, a method, but now this value right there was not given, so it's a smart one. Now the correct substitutions into the formula in general, that's the third mark. The fourth mark is the magnitude with the correct unit. And the fifth mark is noticing the direction, because if you leave it here, you only get 1 mark for the answer. So I hope you guys understand that marks sometimes can be scored in just one step, but in a special manner. Nah. Yeah, man. Yeah. So this is quite a great acceleration, eh? So let's do 3.7, which is the last question here now. It says here, calculate the magnitude, this time magnitude, of the average force that the water exerts on the crate to bring it to a stop. Meaning we want the value of that normal force. So this is going to be Newton's second law in application. So we know that the resultant force is equal to ma, because there's two forces. This is based on this free body diagram. You can say normal force or force of the water, it doesn't really matter, against gravity. And since this one is bigger than this one, so that it's easy to see the difference. Yeah. Now, we will have a resultant force. But remember, we chose downward as positive, right? Right. So we'll maintain that story. Remember, this resultant force is a vector sum of these two. So it's going to be that normal force plus Fg. Right. Which is going to be equal to ma. Now we substitute. Now we know that we have this normal force plus Fg is going to be mass. The mass of the crate is 300 times the gravitational acceleration. It was downward, it's positive, equals 300. The acceleration, we got it. And remember, this acceleration was upward. So what does it look like? Yes, of course, it's going to be negative. We're not substituting this one positive. We need to consider its direction. Be very careful, guys. You will get beat up if you're not careful. This is vectors. Remember, force is a vector. So most of formulas that define vectors, we need to consider directions in our substitutions. Nice. We continue and say that, okay, our normal force is going to be 300 into minus 201,39. Then we subtract 300 into 10. Therefore, our normal force is going to be, and we can see this is negative because it's directed upward. 300 into minus 201,39. That minus 300 into 10. Remember, gravitational acceleration in this one was like this. So this is minus 63,417 newtons. Okay, which is 63,417 newtons upwards. Of course, this one was not necessary. We just wanted the magnitude. But here, I'm interpreting that negative sign because we can't just write it like that. We have to write a positive. Then we account for this, but it's not really a necessity. That's why we're putting it in brackets. It's additional information. It's not required information. Nice. Okay, guys, so this is very easy. And you can see this force really had to be great to stop a mass that heavy. You know, yeah, so quickly. So quickly. So again, guys, this is very important. Remember this. Someone may make a mistake of putting a negative here. You'll be in trouble because then if you put a negative here, then you're wrong. This means if you're saying this is positive, you must put a negative for the normal force because you know it's going to be negative. Okay. So be very careful. So again, guys, you can see the significance of these things. Lama same thing, Lana. Same thing are very interesting and very important. So we get a mark for the formula, right? Yes. Substitution here, right? And showing that this is basically the vector sum. That's another mark. 3 marks. Yeah. Remember, this was a calculation. We didn't calculate the resultant force. This is a calculation. And then this mark is for the general substitutions now. Can you see how ridiculous sometimes the marks are? And then, of course, the final answer with the unit. And you cannot present an answer that is negative. Literally. You don't do that. Magnitude is never negative. but the negative nature is to suggest a direction, but this case is not to be marked. So this is how we score those 5 marks, guys. Nice and easy. So I hope you've enjoyed this one. So this question, we kind of slowed down and tried to spend a bit of time. And you can see certain questions integrate Newton's laws of motion with vertical projectile motion. Sometimes you can get momentum and energy. You know, a whole lot of things can be put in these kinds of questions because they provide for that. Okay. Be very comfortable with this one. So can you see, guys? Easy stuff. Okay, guys. Oh, outside it's raining nicely. This is my kind of weather. Keeps me indoors. Okay. Guys, I've done this question, but yeah, you know what? I'm going to rush through it. I'm not going to spend too much time. So you guys have the Doppler effect for this question. So question 4 is replaced by Doppler effect because this is linear motion there anyway. Now we are told here track is moving forward, whichever that forward is, at a constant speed of 20 meters per second. So this means this track is not accelerating. And there's no resultant force. Now on a horizontal road, Y. Okay, fine. At point X, the driver sees a stationary car 120 meters ahead. Okay, we can see that this distance from there to there is 120 meters. Now, it says now at point Y, so this would amount to his reaction time. I mean, you can see this delta T is between this Y and that X. So this would be his reaction time. Because you wouldn't just see something and then already you're on the brakes. Sometimes you're like, oh, what is that? And then you hit the brakes. So this means he will hit the brakes at Y. Now it says at point Y, after traveling at constant speed for time delta T, the driver applies brakes. Okay, you can say reaction time because he only starts applying brakes right here. Okay, so that time from X to Y is his reaction time. It took that longer for him to think of hitting the brakes. And the magnitude of the acceleration of the truck is 2.5 meters per second squared. Remember, they just suggested magnitude. But what do we know? The direction is in the negative direction. Because this is a deceleration in effect, because we're dropping the speed. If you apply brakes, it's a deceleration. Nice. So we need to understand these things. Again, you guys don't do this section, so you can forget about it. But in the Doppler effect, in any case, you get something similar to this. But they can say a listener is sitting here. This one is hitting a horn. Boop! Move out of the way, sucker. And then you can deal with a question as complex as this, but in the Doppler effect sense. So do not shy away. A question that is very challenging can be created by integrating this into the Doppler effect. So you must be in a position to see these things as they come, because it can hurt if you're not sure. All right. Okay. All right. So it says here, calculate how far the truck travels after the brakes have been applied at point Y until it stops. So stops, it means final velocity is 0. So with final velocity, tinabesbalu V. Then the initial velocity becomes this one. Okay, nice and easy. So we want to know how far will it go. Will it even stop before it hits the truck? Or will it just do it? I mean, hit the car. So from Y, how far will it go with that acceleration, essentially, until it stops? So we don't know whether this is going to be before this car. And as you can see, from that point to the car, it's 2 meters. So will it, usually this is probably where the triangle is, isn't it? Yeah. So will this truck stop before these 2 meters, meaning it won't hit this, or it will stop within these 2 meters? If it stops beyond these 2 meters, then it will definitely hit the car. So this is the question that we're being asked here. So this is a very easy question. We don't have time, but we have the initial velocity, because the initial velocity here is the same. It's 20 meters per second. But the final velocity when it stops is 0. And we know the magnitude of the acceleration. We want the displacement. Easy. 4,1. We know that v squared is equal to u squared plus 2as. This implies 0 squared is equal to, this is going to be 20 squared plus 2 into, remember this one is negative 2,5, that's key, times s. Okay, we can say this implies that our s is going to be 0 squared minus 20 squared, all divided by 2 into minus 2,5. Nice. Therefore, our s is going to be, now let's have a look here, 0 squared minus into 20 squared divided by 2 into minus 2,5, that is just minus 5. So what we get here is 80 meters. So it says now, how far will the truck travel after the brakes have been applied at time y until it stops? We can say therefore the truck will travel 80 meters before it comes to a complete stop from point y. Nake bantakwethu ndafundiswa into yokuba awubuza umbuzo uphendula ngokupheleleyo, awubhala iTelegram. But again, you guys do whatever you are told. Your teachers tell you everything that you need. Asiyeni ngengo, how do we score these 5 marks? First, we get a mark for the formula. Knowing that when we say stop, it's 0. That was a mark. Obviously, guys, we're writing for 200, not 150. So marks had to come from somewhere. Okay? And then correct substitutions in general. That is 3. But knowing that this is going to be substituted negative, that gives an extra mark. Can you see we have 4 marks right there? Okay? And 1 mark for the answer. I mean, whether you mark it there or here, it's not a big deal. Since we chose words here, I don't know why it cut the F there. Sendifuna ukuyibhala in words, meters, before it comes to a complete stop from point Y. I mean, one can get a mark here, one can get a mark there, but it's a nice thing to always conclude your statements. So we get our 5 marks. So not really a difficult question. Usually this would be a 3-mark question, but because there are some things, so a bit of extra marks was considered. Let's do the next question and seal this off. It says when the truck actually stops, it is 2 meters before the car. Now it means this is 80 meters. So this means, yeah, well, it stops before, so it won't hit. It says now determine the time interval t, delta t. What was his reaction time? Okay, nice. So this is very easy because we know that this is 182 meters as a whole. Now from 120, we will know this displacement. This is going to be 120 minus 82 meters. This gives us 38 meters. And remember here we were doing constant velocity. So the trick was just this calculation. So because we know here S displacement is equal to velocity, which is the constant velocity, multiplied by time. So this is the formula that we used when there's no acceleration. Okay, great stuff. So that's just as easy as that. And remember, this came from ut plus half a delta t squared, or just at squared. Now when a is 0, this whole thing becomes 0, and that's how this comes about. So you can use the entire formula if you like, or you just zoom in into that one. It is accepted. All right, not a big deal. So what are we going to say, guys? We will just say, well, we know that the displacement is going to be the velocity times time. Okay, since this time it was indicated as delta t, we can write it like that. But now what would be the displacement? It is going to be the difference between 120 minus the sum of 80 plus the 2 meters. Okay, great. Great, so this is very important. And this is going to be equal to the constant velocity 20 times delta t. This implies that our delta t is going to be equal to, now it's that whole shenanigan there, which is 120 minus 80 plus 2, all divided by 20. Therefore delta t is equal to, this is simply 38 divided by 20. So this is 1,9. This is 1,9 seconds. Very easy. So this is interesting, guys. Again, easy 5 marks. The most important is this determination, right? First of all, the formula chosen is an acceptable formula. That is a calculation on its own. Okay? Then we can say the correct substitutions into the correct formula. That is also important. Okay, all right, okay. And then the answer. 2 marks. And remember, this is a scalar quantity, so what is important is to show seconds. Sometimes I don't trust my S. I can't put my S there because it may look like a 5. So yeah, as to where these 5 marks came from, maybe we can say, look, instead of just giving 1 mark here, because this is a serious thing, remember we had to calculate those two first and then get the difference. So that would be 2 marks. And then the final answer, 5 marks. Again, a gift from the examiners, because this is as good as 3 marks. At best, 4 marks. Okay. So, of course, one can use this equation. S equals ut plus half a t squared. And, of course, you do the same calculation there, but because there's no acceleration, it's 0. This one goes away anyway. So you will end up with that same thing, and then you do your calculation. Maybe that's more appropriate nowadays, because I don't see that formula being given, but we had to know it by heart anyway. Nice. So guys, this is very easy, and we leave it at that. And again, does it make sense that for 38 meters we'll have traveled for 2 seconds? Think about it. We're covering 20 meters in 1 second. 20 meters in 1 second. Now, 38, if you look at it, it's almost 40 meters. Remember, we're doing 20 meters in 1 second. So this is almost double. So this is exactly almost double. So it's 1,9. So this answer makes sense in the given scenario. So we know, even if we have doubts, this is correct because it simply says definitely to cover 38 meters, we should do it within 2 seconds, because in 1 second, we're doing 20. 38 is almost double of 20, isn't it? So guys, again, if you are a math student and you love interpreting things, you will start to feel like this thing is a joke, because this exam looks difficult for someone who's sitting and writing it and has never seen it before. But when you see me do it, you may see that, this thing is weak. It looks weak, trust me. There's a lot of catching you here. You may not get full marks as easy as these questions are, because there's a lot for you to consider. Okay, otherwise it's a fairly simple question paper if you think about it, but there are some areas of some serious thought and integration. Okay, let's move on. So guys, we will have sealed these easy 10 marks here. Again, this was a gift from the examiners to say, look, if you partook in these exams, let's give you some easy questions, although they're not easily, understood, but what can you do? What can you do? Question 5 says, learners at school were required to achieve the following outcome. Learners should be able to use graphical methods to determine how the acceleration of an object. What are we determining? How the acceleration of an object to which a constant force is applied varies with changing the mass. So this is a question on Newton's law. The resultant force, mass, acceleration. So we're playing with Newton's law here. But now, what is the relationship? Can you see the force is constant? So basically the equation governing this experiment is this one. Acceleration is equal to F over m. Right? Knowing that this is the constant, this is best written in a standard format, because this is a linear equation, isn't it? So we will have acceleration is equal to F into 1 over m. Because this is a constant, it makes the gradient. This becomes the gradient of this graph. And we can see that this is the gradient passing through the origin. So literally we see that A is directly proportional to 1 over m. So this is what this means. So this means if A increases, but let's see, we're changing the mass, okay. A will increase if we decrease the mass. And A will decrease, okay, maybe let's choose a different pen. A will decrease if we increase the mass. Okay, that's the proportionality that we see here. Nice and easy. So if you understand the construct and the framework, you already know that whatever this is, it has to speak sense in that framework. Okay. Now, in order to do this, Kashev conducted the following experiment. He first accelerated 1, then 2, and lastly 3 identical trolleys, each one of mass 1 kilogram. Can you see? He kept adding the mass. First 1, second 2, third 3. So this means he increased the mass by 1 unit. Down a friction compensated track. What does friction compensated track mean? Guys, nizobona isingesi ke ba physical science kuyafana nakwa maths guys, isilungu. If awusazi isingesi, hayi usengxakini. As much as I was not best in English, but I understood the language somehow. Strange, isn't it? Yeah. Whatever. Now, a friction compensated track, it means there is no friction. Or is there friction? Okay, so the question is, guys, what do we mean by friction compensated track? Are we saying there's friction or there's no friction? Yikes, yikes, yikes. Technically, because we're saying the force is constant, so we don't want that force to be chowed by friction. So to compensate for friction, remember when you compensate for something, you make up for what would be lost, isn't it? So this means we're just eliminating. This means this surface actually is rough, but we kind of compensated for that friction to make it not to have any effect. That's my understanding, but I could be wrong. You can check with your teachers, but at times in the exam, there's no time for that. But in any case, the way I understand, for this force to be constant, not to change, it means friction must not change. Because remember, if the normal increases, remember for one object, the normal is like that. It's going to be equal to the weight, which is mg. So that would be the weight also. The normal force would also be equal to mg. And remember, if this surface is rough, and then this object has to move in that direction, can you see the friction experienced? As we know that the frictional force is going to be the mu k times the normal. Now the normal force is equal to this. Can you see the friction will keep on increasing if we increase the mass? Because as we increase the mass, the normal force will increase. And that means there's more friction. And that means if we're using this force, the resultant force will be less. But now we want to keep the resultant force the same. Hence friction compensation. So you can even look at some little, work, because as you increase the weight by dropping more weights, that means the normal force will increase and the friction will also increase. And if this force doesn't change, it means the resultant force will be less for the 3 trolleys and maybe intermediate for the 2 trolleys and be the greatest for the single trolley. So in the end, if we compensate for friction, it means we're eliminating friction so that the resultant force is the same. Okay. So this is very great. And you can see this is an incline. So this is to suggest that there is no friction here except for the force applied, which becomes the resultant force. So a bit of thought is sometimes necessary to understand a question by understanding certain relationships, because if you don't get these guys, nizobona umhlola obomvu. Zange ndawubona umhlola obomvu kodwa nizawubona nini. Okay, now it says Keshev used a meter ruler and an elastic cord stretched to the same length. Can you see? Stretched to the same length to avoid differences in the force applied. And at the same angle for each of the 3 situations in order to maintain a constant force. So this makes sense. So this suggests that one can also do this experiment at home. Of course, you would need a ticker timer, ticker tape, and stuff like that, because you know what, it's not that simple. Now it says his results and the graph he drew were as follows. Can you see a table can summarize an experiment? And the graph can help us analyze the relationships. As you can see this relationship? It's hyperbolic, isn't it? We can think of it that way. It's hyperbolic. Now, if it's hyperbolic like that, we know that this is an inverse proportion between acceleration and mass, and that's what Newton's law of motion says. So this is definitely good. It's a good experiment. It's what we expect. Nice. Masiqalele question ke ngoku. If you didn't get that, ukuqala is to begin. Masiqale. Let's begin question 5, okay? Sorry guys, I sometimes forget. I have to keep at the English, okay? Now we can see the acceleration when the mass was less was more, but as the mass increased, it decreased. As the mass increased some more, the acceleration decreased some more. And that's the relationship, an inverse relationship. When one vector increases, the other one decreases, as we can see by that relationship. Okay, all right. Now it says, in order to obtain a relationship between acceleration and mass, it is necessary to plot the graph which produces a straight line tendency. Meaning we want a direct proportionality instead of this graph. So this means we want a graph like this. It's our funny. Remember, acceleration we cannot modify at this point, or maybe we can if we want, it depends. But what we normally want is to do the mass like that. Then we'll end up with this guy, because that proportionality says acceleration is directly proportional to the reciprocal of the mass. Now if we do that, it means this is going to be a straight line, because we want that. This is somehow a bit silly, but if we modify the mass a bit by taking the reciprocal, we definitely get what would be explained by the Newton's law of motion. And this is exactly the setup. It says now draw and label a new system of axes which should produce the straight line graph. Do the necessary calculations. Uzofa mntwana isikolo. Leni question iseka yayibona iyacula. Do the necessary calculations and plot the points and sketch. So I mean, these are easy marks, but it's labor intensive. So guys, mina ndizoyenza fast, but ndizonichazela uba ndenze ntoni. Khawuthi ndibe ndiyofudumeza nokutya ndilambile. Alright guys, so there is my sketch. Okay, I hope you can see it. I just had to connect my phone to the charger. It was dropping its power. So obviously if we produce that line, we can see it will cut somewhere through the origin. I mean, it's not the best depiction, but as long as we get a straight line, we are good. It looks like it. May not be accurate. Obviously, there would be a grid provided sometimes. But if it is not, we just draw our own grid and we try our best. But we should see some sort of a straight line coming up. Obviously, certain things are not going to be exactly as we wish. But for me, I needed to include these calculations because these ones were not there. Oops, that one is wrong. This code, oh yeah, it's correct. This is just 1. Okay, so that's good, guys. So I hope we are clear here. Everything works out nicely. So we were told here, draw a labeled don'ts. So what do we say, guys? What is the topic here? This is the acceleration versus the inverse of the mass. So we need to write a topic. Remember, guys, every graph has a topic and the axes must be labeled. So do not find yourself not doing this. Not doing it is a crime. Oh no. Let's ground it some. Not doing this is a serious crime. So this is the graph of acceleration versus 1 over the mass. Okay, so this must be there. Everything must be systematic. Okay, all right, okay. And then we do the things that we're supposed to do. In fact, we can take this and write it. So nhlanyisa wena. Useka wanhlanza wena. That is the one. So it is good. So 5 marks, guys. So remember, these calculations were important. First 3 marks is just the next thing is the shape of the graph that comes up. That's the 4th mark. And the 5th mark is everything nicely put. It's a bonus mark, isn't it? Nice and easy. So we got our 5 marks nicely. So let's get this question chowed fast and furious. So 5.2 says state the relationship between the acceleration and mass m. Remember, we're not talking about the reciprocal of the mass, but mass m. That is an inverse proportionality. Okay, it says state the relationship. Maybe we can put it nicely. Instead of being hooligans, we can just say acceleration is inversely proportional to mass of object. The most important is the inverse proportionality. 2 marks. And of course, you can even guess this from Newton's law of motion by just the definition right there, because this is it, isn't it? 5.3 says, determine the gradient of the graph sketched here. Now we've got any 2 points. So let's see gradient. What does the gradient represent, by the way? The resultant force, because our governing equation told us that the constant here is the gradient. Can you see? So the gradient is going to be the resultant force. So literally this question could easily say, what is the resultant force therefore? The gradient is going to be the difference between the y values of any 2 points. So you can choose the last and the beginning or any 2. It's not a big deal. So let's just choose the last. This is going to be change in y. This is 0.96 minus 0.31 divided by, the change in x is going to be 1 minus 0.33. And bear in mind, our gradient should be in newtons. Okay, maybe let's not even prolong this. We don't want to waste time. Therefore, the gradient is what that is. Okay, let's do it. Nice and easy. So obviously here there would be some range of answers because a lot of problems can occur. Okay, so minus 0.31 divided by 1 minus 0.33. Okay, now this gradient to 2 decimal places is 0.97, but remember it represents the force newtons. That's the most important. Yes, the gradient doesn't have units in reality, but when applied it has units. So there's a catch in this question. Be very careful. Of course, guys, I've chosen point A and point B. Okay, so those are the 2 points. Maybe let's even indicate the fact that that is what we did, to not be like hooligans. Okay, so let's have a look at this. We can say technically gradient is going to be equal to y at B minus y at A divided by x at B minus x at A. This would imply the situation and the conclusion. Just to try and be systematic. Don't be a hooligan. Although you can be forgiven in physical science, but I don't want to forgive you. So let's not even get to this nonsense. Because for 3 marks, guys, we need some equation, substitutions, and the answer. Remember, the answer must carry the unit of measurement. If you didn't notice what the gradient represents, you are dead for the last mark. Nice and easy. Okay, this is a question on what would look like an experiment. Now, let's see. I'm just going to squeeze these ones here. 5.4, so that I can just end this question in this page. Now it says, what physical quantity does the gradient calculated in 5.2 represent? It represents what? The constant force or the resultant force. We can just say the resultant force. The resultant force. Sometimes you can even say the constant force, because that's the force that we spoke about. But it is literally the resultant force here. And easy 2 marks here. Can you see? The last question, 5.5, this is for you guys. For you to play with. And we know that F res equals MA. But now state it in words. Okay? State it in words because that's the statement right there. State Newton's second law of motion in words. I've just given it to you in symbolic form, but I don't need to state this one. At this point, we just need to salvage our time. So, essentially, guys, we would score those 2 marks and maybe 3 marks because first, it's just the statements and the 2 proportionalities. So we should walk away with these 15 marks. Of course, this is an easy 15 marks, can be done within 7 minutes. But obviously a bit of thought you can see is necessary. So maybe it can take you 10 minutes up to 15 minutes tops. But again, when you're doing this really ready, you know that some questions are easy to answer. Some questions are just, a walk in the park. Great stuff. Let's change the template a bit. Aye, when funwenzani elagagbi. So yeah, guys. Hey, I'm changing. Let's probably again. Next question, question 6. Okay, question 6, this was energy, power, what, a pendulum. Sometimes this question is interesting. Now it says learners at school are given a task to determine the resistance offered by a liquid when a ball moves through it. Now it says Antara and Esha design a pendulum consisting of an iron ball. Okay, what is important though is the mass of 1.5 kilograms attached to a light inelastic string, and therefore it means whatever. The tension is the same. And they allow the pendulum ball to swing through the liquid as shown. Okay. Now the ball is released from point A. Okay. Which is 6 centimeters above its lowest point of swing, which is C. Right. It enters the liquid at point B. You can see that, which is itself 20 centimeters above its lowest point, which is C. Can you see here we have a situation? This question is going to cause you pain if you're not careful, so let's go through it nicely. Okay, now I told you the 2 learners observe that the ball passes point C. And comes to stop at point D. Now, if it stops, what does it mean? Kinetic energy is equal to 0. And that means the final velocity is also 0. Nice. And what does that mean? It also means the potential energy is at its new best. We can say new max, because that would be maximum when we don't have kinetic energy. So we can see here, this is something that combines mechanical energy and wara. This is just work, energy, and power, essentially. Nice. Okay. Now, what is going on here? It says a point below the surface of the liquid before swinging back. Okay, so after this it stops and then it swings back. But now, does it swing back to the same height? Well, we don't know. So this question is a bit what are you trying to tell us? You are trying to tell us something, but we don't understand. What is this something? If there is something that doesn't make sense, it means we just keep it on hold. We do not try to say more. Because if we try to say more or assume more, we're going to run into problems. We can't park the car there. It's not the parking bay. You understand? Verstand, J. Ja, man. J moet verstand wat X. Let's not say too much. I'm going to try to say crazy things. Afrikaans, I wish I knew it, guys, but hey, I don't. I'm trying it. I probeer leer or probeer praat. Ignore the effects of air resistance as this, what? Ignore the effects of air resistance as well as the insignificant rise in the level of the liquid. As we know that, of course, when we put this thing in, the liquid is going to be like, whoa, that way, and then whoa, that way, and then whoa. But we're saying this is not important. Doesn't help us. It doesn't help us. The horizontal vector to all of that swinging motion or the torque or turning effect. Those of you who do biophysics or physics at a high level will be talking about torques, the turning effect. At angular acceleration, situation of the water, we just focus on the single vector that is horizontal. It literally doesn't change. That's what they're trying to suggest to us. Honestly speaking, I am a little bit confused. The string remains straight through the motion, so meaning it's fully taut. So the tension on that string is the same. That's the idea. Now, folks, state in words the principle of conservation of mechanical energy. I mean, guys, these are just easy marks. Can you imagine? 3 marks. This is a 2-mark question because there's nothing special here. Well, we're right. We can say the total mechanical energy in a closed system is conserved, or some persons can say constant, because basically conservation means we keep it the same. That's all. Right. K is total mechanical energy. K is a closed system and K is conservation. So this is how those 3 marks come about. But often this is just combined into just 2 marks. Easy, straight, and 2 BS. Okay, all right. Okay, 6.2. We are told to determine the kinetic energy of the ball when it enters the liquid at point B. Nice. Now this is before the resistance, isn't it? So this is very easy. We can use conservation because remember, within the fluid we have no conservation of mechanical energy. So it's one of the problems that are coming to give us chest pains, isn't it? Brace yourselves for what is coming. Here, easy marks. So we know that mechanical energy at the top, okay, maybe we can say ME at A must be equal to ME at B. That is just conservation of mechanical energy because we ignored air resistance. So that's a closed system, so to speak. So there at the top, it's just potential energy because it is at rest there. Remember, we said this ball is released. So if we're saying released, it means the initial velocity was 0. So we do not have kinetic energy there. So I'm not going to waste my time and write kinetic energy. I'm just going to say mgh at A should be equal to mgh at B plus half mv squared. But now we want kinetic energy, so we don't even need to write the formula here. We can just write EK at B. Nice, because that's what we want. Nice and easy. Why the other one is 0? I'm not interested in writing that thing. It's a waste of my time. What was the weight of this thing? I mean, the mass was 1,5 into G. Remember, we used G, that was 10. The height, it must be in meters. So this is going to be 60 over meters. I mean, centimeters to meters is divided by 100. If you forget, you go King Henry died miserable death common to mankind. Now this means it's 1. 1 millimeter is 1, but 1 centimeter is 10 millimeters. 1 decimeter is 100 millimeters. Oh, sorry, let's put it this way. This is 10. This is going to be 10 squared. This is going to be 10 cubed. This is going to be 10 to the 4 hectares. Is going to be 10 to the 5 kilometers. It's going to be 10 to the 6. So if you master this, you will not be able to suffer if you forgot that you divide by 100, because how do you do it? You cross-read. This is now in centimeters. We will say this much centimeters is equal to this much decimeters. So we just simply say 10 squared centimeters is equal to 10 decimeters. But now we want 1 decimeter, so we divide by 10 squared, divide by 10 squared. This is out, okay, so we know that 1 centimeter. Hey, there's this noise, man, that I keep hearing. I wonder. This is equal to 10, okay, this one takes the square. This is basically 1 over 10 decimeters. Right. Hey, why am I talking about decimeters? Yeah, when we want to go to meters, aye man, ish, fits. Aning mele kancane. Yabona wasenpopeni nibhayisiswa yile ngqondo endiyivayo actually. Yanibhayisisa big time. So we want meters, so we cross read 10 meters and 10 to the exponent 3 centimeters. So we cross read. Remember that. So we're going to say here 10 cubed centimeters must be equal to 10 meters. And then we divide because we want 1 centimeter. So we eliminate that. So that one is out. So we get 1 centimeter is equal to, that 10 takes this one and leaves a square. It's going to be 1 over 10 squared meters. So do you see, we literally just divide by 10 squared, which is 100. So this is how we do these things. This is how we do these things. You understand? Nice and easy. So we are converting 1 centimeter to a meter. Now what would be 60? 60 is going to be the same thing. This is what we do. So it's very interesting. It's interesting. So now, of course, this is a long calculation if you think about it. If 1 centimeter is equal to 1 over 10 squared meters, then what would be 60 centimeters? You put x in there, then you cross multiply. You see, we cross read first to create a bit of an understanding. This is when you don't remember, of course. And then you cross multiply here and solve. So what you will notice is that is x times 1 is just x equals, now you put an equal sign. This is going to be 60 times 1 over 10 squared meters. This is as good as 60 divided by 100, isn't it? Nice. So this is how we do it. If you forgot, obviously, there's a way of dealing with this without panicking, because sometimes you don't remember these things. But it means you should not fail this thing. There are ways of just dealing with the problem. However long it is, we just deal with it. Now this is going to be equal to m, again 1,5 into 10. Now the height at b is 20 centimeters, so this is going to be 20 over 100. Okay, great. Now we're going to say plus ek at b. Now we can see we want to make ek the subject, so therefore ek at b must to can be equaled. Isingesi sisimoshe sasigqiba kanjalo, 60 over 10. Then we subtract this guy into 10 into 20 over 100. Isn't it so lovely? It is indeed a lovely thing. It's a lovely thing, Didings. So let's do it. 1,5 into 10 into security divided by 100. This one, and then we subtract this one also. 1,5 into 10 into 20 divided by 100. Do you see this one is nice like this, man? It's not ideal. I'm getting a very nice number there. It's 6. Remember, this is joules. Nice. So whatever we did, we just did it. So we see that that is 6 joules. So the nice thing was that we had to use the conservation of mechanical energy, which was being asked in there. So this is great. Okay, guys. So this is a calculation on its own. We just didn't want to do it separately. This is also a calculation on its own. We didn't want to do it separately, right? Then the general substitutions. And technically, one can even look at those conversions as perhaps where the marks are, because the rest is pretty straightforward. Ne? Yeah, but those are the 4 marks, and then the 5th mark is the answer. Remember, kinetic energy is a scalar quantity, or energy in general, it's a scalar quantity. But we need to write joules. If we're missing the joule there, we don't have the marks. Very easy question. Hey guys, I'm taking too long, ne? Yeah, I'm becoming crazy now. Last question here says, says the ball moves up to point D during its first swing, as indicated in the diagram, right? Right. Now it says calculate the work done by the liquid on the ball from point B to D. Now guys, you know the work energy theorem that you do? Oh my goodness, because there's going to be friction here. So now this formula of yours becomes the very best. You get me? But Tina, bantu bakleva bakdala sasazba sizothi lento lena, the work done is the change in kinetic energy. Okay? Change in kinetic energy. So if we get the change in kinetic energy, we are done. Because that would be the work done, isn't it? The total work done, or the net work done by the water, would be the change of kinetic energy from point B to D, because it changed from that to that. So this is, one of those questions that is a bit naughty, but it's not that naughty. So if you understand what is cooking, you can do it. But if you don't understand what is cooking, then you just want to cry. Please cry. And this question can be extended to even calculating the force applied by the water onto the damn ball to stop it. What is the work done by the water? We can get that. The work done by the water is literally this one that we want. And if we get that, we can look for the force if we want. Now, this is non-conservative forces. You can use that formula. It's nice and easy. So there's many options to do this question. In fact, maybe we have to explore that. Hey, but guys, ndilambile ask what I must have been the question this or yours. Ndifuna unibonisa ba ezi formulas zena azikho special bafethu ziyaspana qha, that's all. Now maske siqale ngalandlela yamendala yabona. So we know that the work done by the liquid is going to be the change in the object's kinetic energy. I know this. It's like this, most. There's nothing else. So this means the work done by the water or the liquid is going to be equal to the final kinetic energy minus the initial kinetic energy. Okay, easy, 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 easy. Now, the initial was when we got into the water, right? So this, I don't know when balalento man. Sifele siyeke kanje, suka wena man, semphambanisa. Let's siqhubeke in the equal sign. This is half m v squared minus half m u squared, isn't it? But besebenzisa ezazinto yabona, susa yonke nyaka siyifuni. So this is half into the mass. I mean, we know the kinetic energy at B. Do we even need to calculate it? We don't, guys. Ngelinye ixesha xa sekulungile vele ufake yonke lento. So substitution here, this is 6 joules minus. But now at D, we know that it's going to be 0 because there's no kinetic energy, is 0. So the net work done is exactly 6 joules. Therefore, the work done by the water or the liquid is nothing but 6 joules too. But in any case, you can understand that technically we were at 6 joules there and now we're at 0 joules. So this is good. So, I don't know why 6 marks, guys. I really don't know. Because this is the formula, right? Right. This is the substitution, right? This is another substitution, right? This is the final answer. The final is the other way around. Yeah, man. I know there was a catch in the answer. So in substituting nyongo, the final is 0 minus the initial, which is 6. So this is minus 6 joules. Now I think we need to appreciate that this is the negative work done. Therefore the work done is like this, 6 joules, which is equal to 6 joules in the opposite direction. Of course, this is the stopping. This is the work done used to stop this thing. Okay. I don't know, how could I interpret? Maybe we interpret talent. I'm not happy of this one. How do we do it? We can say therefore the liquid did 6 joules of work to stop the ball. Seyigqibile. I mean, you will think this question is difficult. It's not, guys. You see, that is very easy. This being 0, I mean, you don't need to calculate. You can waste your time if you like. It's fine. But there's no need. We know that this thing is 0. Why? Because the velocity at D, it stopped. But sometimes I'm thinking, is this guy for real? I think we're being silly now. Masingaphambani. Sizawusikhabisa nge-examiners here. I-examiners zingakufaka igqudu xa zithanda. Yabona xa zibona bengathi uphambene, uqomba okay lo lihlanya lo, masivele simhlabe ngempama. Siqhela kakubi, cimba le exam kumdlalo lo. So masingabethwa ngempama, guys. It's not right, this thing. We're finding ourselves getting clapped. No, man. No. So this is half of 1,5. 0 squared here. Minus this one we know already from above. We can just put it without calculating it. So that is obanento ecacileyo. So this is a calculation, guys. And the most important thing is knowing that 0 there. More than the rest. You know. The velocity was 0 and therefore the kinetic energy is 0. And the rest of the correct substitutions. So can you see we've got 1, 2, 3, 4. And we write the answer like this with the unit. Maybe the little bit of the conclusion that this was to stop the damn ball. I'm sorry for the expression right there. it means no harm. I'm not too sure. I'm trying to think. Anyway, guys, maske siyeni ke ngoku sisebenzise le formula yenu. This is non-conservative forces because the liquid is applying a non-conservative force, which is friction. So we know that the the work done by non-conservative forces is going to be the change in potential energy right, plus the change in kinetic energy. We know this one. Siyeni ke ngoku. This one is going to be mgh, and this is when balana formula nkhathele ngoku. This is no akho half sunqhela. This is 1,5, which is the mass, into the gravitational acceleration is 10 in this question paper. Be careful, you can be tricked very seriously. The height, the initial height here is at B, right, which is 20. So 20 divided by 100 is what? Is 0,4, right? I think so. Or 0,5, yeah. 0,2, sorry, it's 1 over 5, which is 0,2. Okay, nice. Now, essentially, wait a minute, we're taking the final. The final height, remember, it's just 12 centimeters, so it's going to be 12 divided by, senqamile guys, and senaxesha layo yonke lento. Okay, maske siyenze kahle, sithi ngo-12 divided by 100. Okay, singaphambani. Minus the change, remember, it's negative, so this is all together. Minus 1,5 into 10 into the initial there was now 20 over 10. Over 100, sorry. This was together forever. So now we have these ones. It's going to be half. Mass is 1,5. The velocity is 0 squared minus half into 1,5. The velocity there. Do we know the velocity? Hayi man, ndibhalele ntoni le? Andidingi ukuyibhala le. Siyithatha from that calculation ngo-6. Nice and easy. So masibone basithola bani. Therefore, the work done by the non-conservative force, that is the water, maske siyibone basiyayithola bafowethu. This is 1,5 into 10 into 12 divided by 100. Yazibona mase izinto zinjani, sithi minus 1,5 into essentially, technically, ndiqale kanjani khathi ndiqale kahle, bracket 1,5 into 10. Ndiyacinga uba izawunikeza i-error, ndiye ndancama. I kind of rushed into the thing. And a wise man said, only fools rush in and get into trouble. So fools in physics must not occur, okay? If you are doing physics, you're already not a fool, so don't act like one. Then we add this one. That one is already going to be 0, guys. And funa bendi sokolisa 0 minus 6 joules. So kwenzeka ntoni phayana? Hey, uphume enye impendulo pha. Minus 7,2. Hey, 10 ngathi ndibale zomqala nje. Wena ima kancinci. 10 izoba minus 7,2 ngoku. Hayi. Ayiphumi le mpendulo ngokuphuma 7,2 joules, guys. Yeah. Theni ngathi khona into endingayifumani kakuhle ngoku, andiyifumani man, andiyifumani. Ndifuna ukucinga ke ngoku. Why are you not coming out, sir? Because you're supposed to come out like this, you know. You know, now I'm trying to figure it out. Did I do the right thing? Phayana. Because ibonakala ingathi khona inyakanyaka. I mean, let's maske sijonge formula. Ithe ngathi ifuna ukunijija nje ngoku. Ifuna ukundenzani, iza kundenzani. Ayikwazi undenza nto mos. Yo ayikho kwale formula apha. Ithe ngani ifuna usiqhela nje. Hayi guys, andazi kutheni ke ungathola impendulo. Ibingafanelanga masungaphumi nje. Ibinyanzelekile iphume. Khona into endingayiqondi. But ke guys, I mean, u7 no6 yabona mos akho ndingako. Iyaxelela nje uba apha siyi-underestimate, but is there a problem? I think the problem is neglecting the potential energy change, you know. I think the problem is there. But that's the definition. Why must I get two different answers? Why am I not getting Sigiza? Because I'm supposed to get Sigiza, you see. So there is something not adding. But in any case, there is some potential energy there left. It also changed. So the question is it safe now to write it like that? Yewen. Hi guys, andizingeni ne? Asiziyekeni khona. Sigqibile lento lena. So singabhala the same conclusion ke ngoku. Yho, ndiyonqena ubhala. Cela siyikopeni. Ezi zinto ziprovida ubumncwane. Ubuncwane bemvomvo. Wakwayifunda lo ncwadi? Anizazi ezo ncwadi. Sasifunda isiXhosa esibhadlileyo ke thina. Anyway guys, certain things are in overestimation, others are in underestimation. At the end of the day, this one we can just write here. This is 7.2 joules. I think it depends on the approach at this point in time. You can see the difference is not that big. They are quite close, so I think we can accept it. If not, please go to bafethu ngicela ni verify le. Kanibuzeni ngotitshala uba into enjithi 1. Yabona, because iba khona ingxaki somewhere along the way. But these questions are not really perfect, are they? But anyway, for me, I'm happy with the approach, so it should be fine. So again, if you guys can obtain the memorandum here, you can get the marks. But obviously, questions like this get you thinking, but am I right, am I wrong? But it's a slightly higher grade question, this one. It's an inclined in that direction. It's inclined, not it's an incline, but it's inclined in that direction. Okay, guys, now I'm losing time. So we can see the 6 marks there. It's 1, 2, 3, 4, 5. Yes, 6 ivele ke ngoku. Sifumene phe yes 6 mark. 1, 2, 3, 4, 5, 6. Okay, this 6. That's easy. And then of course, guys, this calculation on its own, this one was new completely. This one was done already, so we're not gonna give a mark. This one was new. This one was was done already. So this is 2 marks already. Then we can say general substitutions makes up the 3 marks. This is the 4th mark. This is 1, 2, 3, 4, 5. Well, perhaps the 6th mark is for this conversion because that conversion is significant. I think that's the most important. The rest is whatever. So at the end of the day, guys, we score the 6 marks anyway, however we look at it. Sometimes the answers are not perfect, but if it is close to what I got above, I will accept it. But be careful, look through your teachers for confirmation, or at least find the memo of this paper, and hopefully the official one will then, resolve the problem. Okay, guys, I'm taking too long. I didn't want to do more than 4 hours, actually. but I started stalling. I mean, guys, these are easy questions. Again, we just simply go about it. I think I'll do some skips, okay? But I don't like a memorandum that skips around. I think some challenges are coming here with electrostatics and parallel plates, maybe here as well. But that would be it. So we have 2 more questions to go once we challenge this one. I think, guys, what I need to do is to take a break. I think I need to meet my student. And I need to do some physics with her as well. So maybe let's pause here. We will come back later. I'll use my other phone for the lesson. Okay, guys, so I am back. So essentially, I had to meet one of my students. So I had planned to meet them for electricity, especially current electricity, because they were struggling with this. So we handled some past exam question papers on that. I'm sorry that I had to pause this for quite a while, but in any case, it's not like there is a student online at the moment, is it? Because you guys don't join. No matter how much I give you these links and I do these sessions, you guys don't join. But anyway, I wish you would join, because these could even be discussions that are even more fruitful, because you get to ask questions as I do these memos. But anyway, whatever. So now I'm back, but I'm a bit tired. I don't know. We've got how many questions? 2 more from this one. Okay, let's try to squash this one, because this one is on momentum. It's very easy. Now it says Hendrik is an amateur rocket builder. He launches a 2-stage rocket as shown below. Section A, which is stage 1. Right. Contains the rocket engine and fuel. Okay. Now section B, which is stage 2, has the mass of 2 kgs. Okay. Nice. This is like a bullet. I don't know what this is doing. Now it says Hendrik says that Newton's third law of motion, used to explain why the rocket moves upwards. Now it says identify the action-reaction pair of forces involved with the launching. This is interesting, eh? Now, Hendrik says that Newton's third law of motion is used to explain why the rocket moves upwards. And that's true. Definitely true. Now it says identify one action-reaction pair of forces involved when launching this. So remember, when we launch this thing, remember at first this thing is in contact with the ground, isn't it? Now the force of the ground on the rocket is going to do that thing, and the force on of the rocket on the ground. Can you see? Now those are reaction forces, because we've got the ground and we've got the rocket. So this is the force of the ground on rocket, and this is the force of rocket on ground. Hey, balaga agbini. So this is what is going to happen. So this is the force of ground on rocket, and then this is the force of rocket on ground. Can you see? Those are action and reaction forces. Again, remember, for the rocket to launch, there's an explosion that takes place here. There's gases here. So this could be the force of the gases on the rocket. Again, that is another pair. force of gases on the rocket. And then we could also have the force of the rocket on the gases, because for them to propel this, there has to be that. But depending on which one is lighter, this is what leads to what we see. So this would be now the force of the rocket on gases. Can you see? That's nice. So this is literally what is cooking here. But of course, the intermediator here is the exploding gases here. Because these exploding gases are going to have this force applied on the ground, and the ground is applying an equal force on the rocket. And because of lightweight, this one is going to launch upward, but the ground is too heavy. It won't move, okay? Or at least significantly. So that is the story, guys. So now it says identify any one action-reaction pair. So here you can choose any one. We can just say it's the force of ground on rocket paired with the force of rocket on ground. Okay, any one pair, but you can see there's two pairs that we can consider here. So you get a mark for each one of those pairs. So easy stuff. So we can answer this one and say 7.1. We would have force of ground on rocket paired with force of rocket on ground. And remember, action-reaction pair of forces acts on two different objects or two separate objects. They are not on the same object. So that's the key. So easy to marks. Nice and easy. 7.2 says, now it says at a certain height. Don't know what this is. It is probably a question. When the rocket has a velocity of 5 meters per second. Now we can choose a direction. Remember, with momentum, we need to choose a direction. So we can choose upward as positive. This would mean downward is negative, okay? The last fuel is used up, and section A is used up, and section A then has a mass of 3 kilograms. I don't understand this question a bit, but it's starting to work on my nerves. At a certain height, when the rocket has a velocity of 5 meters per second, okay, the last fuel is used up. And section A has a mass of 3 kilograms. Okay. This means 3 kilograms plus fuel weight. Fuel weight or mass. But now the fuel mass is lost here. Okay. So this one has 3 kilograms. So this means section A alone without fuel is 3 kgs. But with fuel, it's more than 3 kgs. So this is the understanding that we get because these two were added together initially. Okay. Not a problem. It says to get section B even higher. A small explosion separates B from A. Okay, so that means the fuel is taken out of the equation, so we don't have to worry about the fuel. Okay. Now, we know that to get section B even higher, because that's what we need to send away, a small explosion separates B from section A at this point and increases the upward velocity of section B to 8 meters per second. Okay. So nice. So at first, before the explosion, now remember this explosion here is insignificant at this point. But the last explosion, it's when we are only dealing with this mass and that mass. Ne? And now these two separate through this small explosion. And we know that the velocity, remember section B initially was moving at the same velocity of 5 meters per second. But now it increases to 8 meters per second. See, sometimes the question can be quite busy and make you lose your brain. That is how examiners try to play with your mind. But at the end of the day, if you listen carefully and you keep following, you understand certain constraints to be eliminated and certain constraints to be added, then you get to understand what's cooking. Okay. Now, what are we saying here? This is the story. So now this is exactly what is cooking. So this is after explosion. After second explosion. Now this would be before this would be the first, before the second explosion. So this scenario is before the second explosion. And the velocity here that these are moving at, we can call this one initial velocity, is 5 meters per second. But then this is the final velocity of the section B. But now what would be the final velocity of the section A? We don't know, and probably that would be the question. Now the question says, state the principle of conservation of momentum. Easy 3 marks. We know that the total linear momentum, the total linear momentum in a closed system. Sometimes the word isolated was used as well, but this is nothing but another synonym, so to speak. Say in an isolated system remains constant, or we can say is conserved. So play with the English, guys. Be flexible, but please make sure the understanding is solid. So how do we get these 3 marks? Obviously, total linear momentum has to come in. Good. A closed system or an isolated system has to come in. It has to be conserved or constant. Easy mark. So every single important message sent there was a mark. But again, guys, this was just to try and generate 200 marks for the question paper. Otherwise, this is as good as 3 marks when we take it to 1/5, okay? Now the next question says, calculate the velocity of section A after the explosion. But which explosion? Second explosion. So can you see, when you understand the question enough, you know what you're dealing with. So even though this is vertical motion, we're not interested. Obviously, if this one is pushed up, this one has to be pushed down, right? So our hunch says this velocity is downwards, but we will see. If the velocity is negative, it would mean downward. And remember, the question said calculate the velocity. It did not say magnitude. So we need to consider the direction of that velocity. Now we go 7.3. You saw as saying, we know that P before must be equal to P after. Right. So this is important, and of course, guys, indicate that the upward direction is positive. That has to be said somewhere. Now, what do we say? We're going to say now the mass of B, right, times the velocity, the initial velocity of B. Can you see how clean this is? There's not too many subscripts. Plus the mass of A times velocity of A, initial velocity of A. Can you see? UA. Mass 2 can be equal to mass of B times velocity of B. Can you see how clean this is? Hi guys. Andazi wethu kutheni abantu bethanda ubuxeleka. Uthatha ihagu ikhuphe edakeni yona ifuna uyozifaka edakeni. I'm sorry guys for the expression. It's derogatory, I know. But I know most of you are not going to understand what I just said anyway. But those of you who understand, I apologize. Hey, man, I'm too outspoken, and sometimes maybe I use that as a cover-up. I am obnoxious. Let's just understand that. Toxic. That's me right there. Now B is 2 kilograms multiplied by the initial velocity, remember, was 5 for both, plus, in fact, we could easily just add these masses because they were together there. They are moving together. At some point, let's not even waste time here doing crazy things. Let's just do this. The initial velocity was the same, so this is going to be mb plus ma times the initial velocity of both. So we can say just AB. Then here they split because now they're going to be slightly different. All right, okay, so this is now 2 plus 3 times 5. Remember, this is upward, so it's positive. Now mb is 2, final velocity has increased to 8, plus this one is 3, the velocity is what we want. Now we do it. We can say this implies that the velocity of A will be, we transpose that, so this is going to be 3 plus 2 times 5 minus this one, 2 into 8, all of that divided by 3. And you will appreciate that the answer is going to come out negative. So if you did everything correctly, it has to say that. So let's see, 3 plus 2 here, multiplied by 5, that's so, minus 2 into 8 there. And let us see that this divided by 3. What do we see? This one is positive. It is trying to tell us that, yay, we are still moving up, so our hunch was incorrect, guys. Maths get the physics is delela makufewala. So if you put me positive, I mean, this is making sense. 5 times 5 is 25. 25 is greater than 16, so the answer is positive, guys, and it's a positive 3 meters per second. Now, if it is positive, so we can say, therefore, the velocity of A is 3 meters per second. If it comes out positive, this is upwards. So that was not enough to drop that velocity into the opposite direction. The explosion may have occurred, but it just dropped the 5 initially to just a 3, but still in the same direction. So a very nice question. Can be tricky, but of course you need to anticipate some things but correct yourself if it comes out differently. So we get a mark for the equation, and please take note, we chose a direction. If you don't choose a direction, this answer can be a nightmare, okay? Now, this was a calculation on its own, right? Right. So the rest is, okay, maybe that was a calculation on its own, and perhaps this one is also, the right-hand side is some sort of a perhaps let's say this is a calculation on its own, and the rest of the general substitutions. Yeah, looks like it. It looks like it. So we've got how many marks? 1, 2, 3, 4. Then 5 for the magnitude, together with the unit. And we needed to specify the direction because this is a vector and no one said magnitude. So if the question says velocity, we need to consider the magnitude. Okay, guys. Anyway, however these 3 marks come about, they are there. So this was just a gift from the examiners again, guys, because I mean, this could be easily 4 marks at best, or perhaps 5 if one wants to be generous. So this one was an extra mark just in case, you know, most. Now, guys, you don't do parallel plates and stuff like that, but hey, I'm going to do it, okay? I am doing it so that if it gets reintroduced in the near future, because I'm not too sure, guys, if I'm going to keep up posting videos anyway, but I'm just going to post everything that I think of. Because like I said to you, I tend to be a witch doctor. Sometimes I can tell when something is coming. You may find that these questions may be relevant in the next 2 or 3 years. You never know. And who knows, I may not be that active at that time because I'll be busy with other things. Or if I'm still active, I'll be very rarely active. So in a way, these videos become an important bank of knowledge for you guys to just keep bouncing on and taking as much as you can. And hopefully it makes a positive impact in your life. Now let's do it. Of course, for now, you probably want to not look at this question at all. You probably want to pass through. But let me warn you. Do not take anything you come across for granted. If you had enough patience to go through this video until this question, please don't skip. Because you don't know when this question can actually be asked. Remember, the examiners can ask you anything. But they can provide you a little bit of extra information here. Enough for you to be able to deal with this problem nicely. So do not be fooled by the fact that this is not normally part of the curriculum, but most of the calculations are within your curriculum. It's just that it's the setup that looks a bit different. But different doesn't mean foreign, isn't it? Yeah. So be careful. Be careful. Don't take anything for granted. You might thank me later for these things. I've done all 4 videos, physics, maths, chemistry, and maths paper 2. And you may think I'm bluffing. You will see what I mean. Either now or in the May June exams next year for those who will want to upgrade or those who still want to further their marks. Because obviously, guys, this thing is a process. You may still get up high but not high enough. And you may want to give it a last push next year. It's okay. So you will thank me for this. Believe me when I say, of course I sound crazy now, but you will tell me about it. If of course I'll be around, because I may die during December, I would be happy if that happens, because you know what? This life is too hard. Oh my Lord, what am I saying to you guys? I'm trying to plant negativity and depression. No, do not allow me to do this thing because it is not right. Because I must tell you positive things, but here's the reality of life. Life is unpredictable, guys. Ukufa kulapha ezinyaweni. So up uyakhona ungafa. So hlala uyazi lonto le. That's why I need to acquaint yourself with that reality. It can happen anytime. And you must not cry about it. Okay? Live the very best of each moment you have on this earth. God is not a fool to give you that moment. Make a positive impact, either in your life or in those around you. But don't be useless. Don't be just a waste of energy. Simply talk. Don't make the graves rich of potentials that were never realized, okay? Realize everything within your reach so that by the time you are dead, you truly go to sleep, man. Okay? And you let all your works that you did speak for your presence that will never be forgotten. But yeah, not all of us are going to be remembered for sure. I'm probably one of those not to be remembered. You know why? Because I wish it so. Anyway, anyhow, too vocal to be forgotten completely. In my inner circles, I'll probably never be forgotten. But of course, in the bigger circle, like the country and the world at large, I am not even known. I know it. I know it. Okay, now a tiny ball of mass, 0.2 grams. Now, once you see grams, you immediately convert that thing to kilograms. Now, that lovely thing there, we divide by 1,000. 0.02 divided by 1,000. Just go. About no 0 by 100. So this is giving us 0.000. Ooh. Let's be 4. 1, 2, 3, 4. Izobange is 5 yon. 2 like this. I imbi. Masipal in scientific notation. It's ugly like this. I don't like it. So this is basically 2 times 10 to the exponent minus 5 kgs. It's a very small weight. All right, so if you don't know these conversions, I mean, you are dead. But remember, King, Henry, Wafa, Ukufa, miserable, bigger cool. Miserable death, okay, okubi ukona ukufa decimeters, but okuqhelekile, okubi ngokuqhelekileyo, common kubantu bonke, okanye kuluntu, mankind in Xhosa luluntu, basically, uluntu. Now, uluntu is millimeters, right? Mankind, 1, this one is 10. We know 10 millimeters is 1 centimeter and 100 millimeters is 1 decimeter. Sorry, Masipale 10 squared. This one is 10 cubed, 10 fourth. This is 10 fifth. This is 10 sixth. So this is how we do it. Now, grams ke bafethu now uzazibonela xa kungu-meter phayana ifanele uba ngu-gram. Then xa ingu-kilometer phayana ifanele uba ngu-kilogram. Uyayiqonda? You just adapt the thing like this. Now, how do you do it? You cross-read again and again. Now, sithetha nge-grams phayana, 2 kilograms. So, this is the thing that we can do. So, we cross-read like this. So, we're going to say here, technically, 10 to the exponent 6 grams must give us exactly 10 to the exponent 3 kilograms. Now, we're going to say 0. Oh, let's do 1 first. We need to do 1 gram, basically, because we can't have 10 to the exponent 6, but you can still use it if you want. I mean, maths is maths. This is 10 to the exponent 6. And then this one does the thing to this one, and that 3 does this one and leaves another 3 there. So we know that 1 gram is given by, basically, actually this one goes away as a whole, is given by 1 over 10 to the exponent 3 kgs. You see this one? And then now we can ask ourselves, what is 0.02 grams going to give us x? Cross multiply, okay? When we do the things, we will realize that x is what we want now. Do you see what is this? This is 1 over 10 to the exponent 3 times 0.02. Can you see we literally are taking 0.02 and dividing by 8,000. So, it's a lot of work, of course. Kodwa, it's enough to get you across the river if you don't know. Because trust me, if you get this in your head, because some methods can be quite nice and very straightforward, and perhaps maybe a bit more simpler. But the thing is, what happens when you forget? Because remember, under the heat of the moment, usually methods that are quicker, they have a tendency to be short-lived in your brain, because usually they are not greatly understood. Unless you've got great teachers like many other guys on YouTube, which I recommend for you to look at. Probably at the end of this video, I'll tell you who to look at, where you can learn the best. I have a few people, but a handful of them, that I think if you're a student who's struggling and you need to understand things better, if you watch videos from those guys, it will be good. And then other videos are good in their own way and they're unique. But sometimes they're not suited for a student who's trying for understanding, because remember, for you to be sure you are going to pass, your understanding has to be solid. If it is weak, you're not going to pass. That's a definite yes. Okay, it's a definite outcome. So please, guys, keep this in mind. This thing simplified my life greatly, because I used to forget what to do with these conversions. But ever since King Henry died, this miserable death common to mankind, I was able to do anything without even wanting to cry when I see a question that forces me to some sort of a conversion. Because if this is strong in your brain, you can do anything, anytime, even unprepared. Okay? So the idea of studying things in this manner is to say, guys, learn ways that actually transcend issues that can be easily a pressure point. You just deflate all of that pressure, because all you have to do now is to speed up. But you are speeding up on something that is easy to grasp and keep, because it's methodical. Other ways can be quite fancy and less methodical. It's easy to lose there if by the time you get to it, you don't remember the process, because a shorter process is not that sensible. It's very easy and convenient, but it's not that sensible, because you cannot read much from it, and you cannot be sure of it if you've remembered it well or you've forgotten. But like I said, guys, if you're taught by the best, which I will tell you at the end of this video, hopefully. I mean, I've been saying these things throughout most of my videos anyway. So you will know that those ones can actually emphasize this right, long enough, or they can emphasize this as many times as is necessary for a student to nail it. Okay, and I don't know why. Now, a positive, okay, this is our ball right there. And this ball is carrying this charge. It's a positive charge of 4 times 10 to the exponent minus 9. This is basically 4 nanocoulombs. Nano means times 10 to the exponent minus 9. All right. Now it is suspended by an insulated silk thread. Now, what do we mean by insulated? Now, remember, in electrostatics, we want the charge conserved. We don't want this to interact with other things so that this charge changes. So we want to keep this charge constant. Hence, we insulate that string, because remember, there could be an electrostatic force between the string and this one. And then this coming together can combine and divide into 2. And effectively, this charge can drop significantly. So we don't want that. Okay. We also don't want this ball to separate from this, because once they carry the same charge, they will separate, isn't it? So we want them together, hence we insulate. So understand certain things and the reasons behind them. And you're not going to read that in the book, right? It's not there. You will look and never find it. So please, guys, read your books, yes, but pay attention to us. Us, the oldies. They will tell you things that are going to, you know what, immensely increase your awareness and knowledge. Okay, and is at rest. It's not moving. But remember, this thing has a weight, isn't it? So it has a weight Fg. Now there's this force, or the tension on the string here, that is suspending it. So can you see, if it is suspended, it's not moving down, it's not moving up. And remember, this is positively charged. What do we expect? There's a force of attraction with this one. So it means this tension is balancing both the weight as well as the electrostatic force of attraction with that plate. Because this is negatively charged here. And again, what is the direction of the electric field? It's downward, isn't it? So this one experiences an electrostatic force due to the electric field down, together with its weight hanging down because it has mass. But then the tension has to balance these two. So the free body diagram on the ball is tension equaling the gravitational force and the electrostatic force, but I don't know which one is big, and I don't care. So that is essentially the story. So guys, be very careful. Newton's law of motion can be asked. You may find that some acceleration can be asked here, of what is the acceleration or the velocity that this ball is moving, or the acceleration that this ball would actually move if you snap that thing, and why. You know, many other questions can be popped here. Very nice, very easy. And again, there's another force, the repulsive force. But again, because there's an electric field here, well, the repulsive force is whatever. We look at them, but sometimes it's a bit of a nightmare. You know. All of that repulsive force actually combines with this one to give us the force that goes down. Because remember, they are both directed the same way. This one is attracting, that one is pushing. So they're in the same direction. So they will add up to this net electrostatic force. So remember that electrostatic force is the net electrostatic force. It's not just the electrostatic force by the plate. It's the net of the positive plate pushing on the ball plus the negative plate pulling on the ball. Since the angle between the two is 0, so it will give us a single net electrostatic force. So be very careful here. The force is the resultant force of the electric field. Yes. Now you get it. Okay, guys, mandiye kuphambana. Asiqhubeke again. Now, bafowethu masiqhubeke again. Ithi ndengo. It rests between two large, positively charged parallel plates which are they are not oppositely. Obesenza athi niyaqhunywa. Nanichayile bafana. Kodwa khawufana ucinge ndidelela abantu abadala, because badala abantu ababhalela iphepha bebadala kakhulu kunami. So ndiyaxolisa. Okay, two large oppositely charged parallel plates which are 2 millimeters apart. Now the distance apart has to be in meters. So if you see 2 millimeters, what do? Divide by decent. If you forget, you cross multiply there and deal with it. So now 2 millimeters is going to be a decent there. So 25 divided by 1000 is 0.025, this one. So this one must be 0.025 meters. We don't accept things in millimeters, so always change these things. Okay, so obviously these plates mean there is a battery connected such that the long one and the short one are like this, because there's a potential difference maintained between these two plates for us to have an electric field. And of course, that one being positive and that one being negative, affecting those plates like that. And we know that the electric field strength here, E, is going to be the voltage kept across these plates over the distance between them, which is going to be meters. So this is going to be volts per meter. Now we can even calculate its magnitude, because what do we have? Oh, we don't have the voltage. The potential difference is 5000 volts. Now we have it. So the voltage across the terminals here is essentially 5000 volts. So that means we can calculate the electric field strength. It's going to be 5000 divided by 0.025. Okay, sometimes some minor calculations can be very necessary. Okay, divided by 0.025. It is important, guys. This is 200,000. It's a very huge electric field strength, 200,000 volts per meter. This could be a question, but again, guys, you're just trying to use whatever you have and you deal with the problem, right? And you can even calculate the electrostatic force here if you want, because this one is going to be FE is going to be equal to EQ. Now this is going to be equal to the electric field. We calculated it now. It's 200,000 into the charge is plus 4 times 10 to the minus 9. Okay, and that's Velevatin Payana 10 to the minus 9. So we can calculate everything here. 2000 times, basically 4 times 10 to the exponent minus 9. This one is quite small. The force is very small. This is 8 times 10 to the exponent 4 newtons. Because that's the force. Newtons. So can you see, guys, a whole lot of things can be done in an instant because you know what is cooking here. You see. Yes, because we cannot quantify how much this one is pushing, so we rely on the electric field strength right here. Interesting. You will love maths applied in physical science. So guys, send Coulomb. It says now define the electric field strength. Do you remember this one? What is the electric field strength, guys? Kaninixeleleni sawusela amanzi ndiyabuya. Hey, suniveza. Hey, ifuna ukundiveza iyangiqhela. Hayi guys, hey wena. Kwenzakalani manje? Hey, angisazi. Hey wena. Kwenzakalani? Hayibo. Okay guys. Okay guys, I don't know what happened there. I started doing crazy things. So this means this thing can actually write on the page as well. I didn't know this one. Okay, can Beni define lapha ngisayo sela amanzi ndiyabuya. Quick. Okay guys, hey. Angigqibi ngo. Anyway, what is the electric field strength again? It is a electrostatic force experienced by a charge at a given point. Okay, because electric field is E equals the electrostatic force per Coulomb. So if you don't remember this, because you need to remember this formula. Then you can just write this in words. It's the electrostatic force experienced by a given charge at a particular point. Nice. It's newtons per Coulomb. Done. Easy 3 marks there. But you can say other things as well that you like, but don't complicate your life saying things that are irrelevant. Now, 8.2 says calculate the magnitude of the electric field strength between the plates. You see? Very easy. And what are we looking for? The magnitude. But the direction is downward or to the negative plate. But now the question is on the magnitude. So 8.1, guys, I'm not going to write it in words. I'm just going to leave you with that. Electric field is the electrostatic force experienced by a charge, a unit charge at a point. Okay, whatever. There's many ways of saying it. But the key word is write it in words. Talent in spoon feed and go. Write in words. Please do not write in symbols. It's no marks for you. But you can write this properly. Okay, write in words, you get your 3 marks. Now guys, I'm just chasing time because I've wasted it anyway. Calculate this magnitude. So we know that E is the electrostatic force. No, we can't use this one. Remember, parallel plates is the potential difference, V over distance. Nice. This means E is going to be, what is the voltage? Is 5,000 divided by the distance. This one is going to be 0.025 meters. Very important. And therefore, our E is going to be what we calculated. 20 square volts per meter. I don't like to write like that. I write volts like this per meter. This is my way of writing, but I'm going to accommodate. Remember, an electric field is a vector. Now we can say towards the towards the negative plate. But at this point, this is additional information towards the negative plate. additional. Just in case, question was saying the electric field strength instead of the magnitude. So obviously for formula we get a mark, correct substitutions, and this conversion is the extra mark, okay? And the final answer together with the unit of measurement. If that is not there, you know what is the outcome for you. 8.3. What do we say? We need to draw a labeled force diagram of the forces acting on the ball. The length of the respective vectors should indicate their relative magnitudes. Now there's the ball. Here's the ball. Okay, all right. Okay, we know the tension is bigger than all of them because it's acting against two forces already. I go straight. Okay, masizame bengathi straight le ndaba utsho sisima brr. Like you do, beg I remember me. You've only my shaka kama land. Brenda faso claribinela. His straight landaba. Claribinela. His straight landaba. Ay. Sisacula iconcerts ngiyafethu ezilalini. Hey, sasicula into ezimnandi. Hayi le nyaka nicula. Cula inyongo nithi talente. Hayi man kancinci. Okay, yayibheda naliyana kodwa hayi ibinconywana. We had serious points of reference, not this rubbish. Anything goes these days. I mean, how ridiculous. Okay, guys, so we can say this is the force of the string. We can say tension on the string. Okay, this is an acceptable label, T. It always represents tension on the string. Now, which one is bigger between the weight of this thing and the electrostatic force? We saw the electrostatic force is times 10 to the minus 4, not 10 to the 4, okay? But now let's see what is the weight here. So this was 2 times 10 to the exponent minus 5, right? Right. Times, now our gravitational acceleration was 10, guys. So we see that the gravitational force came out as 2 to the exponent. So, I mean, this is mg. This is going to be 2 times 10 exponent minus 5 times 10. This came out as 2 times 10 to the minus 4 newtons. Can you see? This one, 2 times 10 exponent minus 4 is less than 8 times 10 exponent minus 4, okay? Great stuff. So we can see that the electrostatic force is greater, so our diagram was not too bad. So we know that the electrostatic force is going to be slightly greater, right? But it can't be equal to that one. So this is the electrostatic force. Okay? And then we can see that the weight is shorter. Eish, perfect. Why it's. This is Fg, or we can say this is the weight, if we like, of the object. So we get a mark for each one of these forces, 3 marks. And then adhering to the instruction that the relative magnitudes have to represent these. So essentially the extra mark is for that. So we get 4 marks. So with higher grade, it was not necessarily a very true reflection of the forces acting, but mainly adhering to some principles and being principled in the process. Nice and easy, guys. So this one is easy marks. See, there were easy marks even back then. Calculate the magnitude of the force that the thread exerts on the ball. Can you see? We want the tension, basically. And you can see this is a bit. This is a bit. But can you see now? Having done this calculation, of course, this was not the question initially, but it helped us to know the different magnitudes of forces acting on the ball. So now, of course, this is the ball. Okay. Now, we understand that we use Newton's laws of motion to get this done. But there are some side calculations that are going to kick in, like Fg, the electrostatic force. So these are side calculations within the calculation. So I'm going to complex these into one single step. But of course, you do this when you are brave. When you're still weak, don't do it. You're going to die. So we know that the resultant force is equal to ma. Can you see in electrostatics, all of a sudden you're talking Newton's laws of motion, because these guys are pervasive. This is like the essence of physics, guys. If you don't accept this or appreciate this, you are dead meat. Now we can choose a direction and say upward. The forces upward are positive. This would automatically mean forces downward are negative. In fact, I don't know why I'm writing it there. Remember, we have to make a choice for every question, but try to be consistent. Do not do otherwise. So we can say, well, upward forces are considered positive. And then we're using Newton's laws of motion, even though we're in another chapter. But hey, it works. So this implies, now remember, this is a summation of forces. This is tension plus the sum of these two forces. This is going to be Fg plus the electrostatic force. This should give us Ma. Now Ma like this, okay? Nice. Tension plus. Now these forces, we know that they are oppositely directed. So this is going to be minus the mass of the object, which we calculated as 2 times 10 to the exponent minus 5 kgs, into the gravitational acceleration. This is 10. Now this one is also negative, because this is plus minus, okay? That's also negative. The electrostatic force, we know that it is QE. So we've calculated the electric field. It came out as 200,000. So you can say this is 2 times 10 to the exponent. How many zeros if we push them away? 2 squared is 1, 2, 3, 4, 5. So this is times 10 to the exponent 5. Into, just to avoid that long lengthy thingies, then the charge on that electron, on that object is 4 times 10 nanocoulombs. Okay? This is equal to the mass, which is 2 times 10 to the exponent 5 into the acceleration is 0. Why? Because we were told this ball is resting. Ah, man. Amen and amen, guys. So this is tension minus. Now we sort that thing straight into BS, but maybe let's just do it like this. We do it like this first. So this whole thing is going to be negative. Okay. So we've got 2 times 10 exponent minus 5 into 10. Plus, these ones are added, right? This is 2 times 10 exponent 5 into 10 into 4 times 10 exponent minus 9. So this one gives us a minus 1 times 10 exponent minus 3 equal to 0. This also implies that the tension minus 1 times 10 to the exponent minus 3 is equal to 0. Therefore, the tension is going to be equal to the summation of these two anyway. It's 1 times 10 exponent minus 3 newtons. Now remember, it said magnitude, but we can still put additional information and say, it's a vector, man. We need to give it respect, even if you don't demand it. We are very good people who are respectful, so vectors must give them respect. These are elders of science. So, yeah. As you can see, in one step I did everything, but you can separate the steps nicely. But I mean, who cares? Nobody does. So first of all, formula, interesting. This is a calculation on its own. This is a calculation on its own. You get me? Yeah, and we can safely say this is the generals, don'ts here. So this is 1, 2, 3, 4. This is 5. So where's the extra marks? Yo, guys in Libel, this one was a calculation on its own. I know we took it from above. No, it was not. But there was something. The mass, the conversion, it's a mark, and the entire calculation. So there's 2 marks there. Okay? Yes. That is key. So we've got 1, 2, 3, 4, 5, 6. And ask you guys, maybe choosing a direction and knowing the sign, whether we mark it here or we mark these signs there, it doesn't matter. But the fact that we account for those signs, that's the extra mark. So it gives us 7 marks. Okay, physics is interesting, folks. I cannot overly emphasize that. But maybe instead of the sign, I think the sign is not really that great, is it? But knowing the acceleration is 0, I think is more important than just that lovely thing there. So perhaps this is how the 7 marks come about. It's 1, 2, 3, 4, 5, 6, 7. Nice and easy. But we've had to do some work, ne? We've had to do some work, guys. Now it says here 8.5. We can already see this is going to be a bit of a situation. Now 8.5 says the ball comes loose. It always happens. From the silk thread, but is required to remain stationary. Assume that the charge on the ball. Assume that the charge on the ball remains the same, meaning it's positively charged. Ooh, these ones are the true higher grade questions, guys. The others were simply standard grade stuff, with the exception of this dude. Okay, because these steps that you have to figure out yourself make it a higher grade, but it's not too bad. But now once things change like this is a true higher grade component that says we're in trouble. But in any case, this question in total, it was never asked in standard grade papers, unless I have forgotten. Millikan's experiment was for higher grade only. Yeah, I think so. All right, now let's go. In which direction should the electric field now act in order to keep the ball stationary? Now we can see that the free body diagram, the electric field was down, and obviously these ones were equal. But now if you break loose, it means the electric field has to oppose the gravitational force. But for this to be stationary, it must be such that the electric field is equal to the gravitational force. Understand? Yes. But now for this to be the case, it means these plates must reverse. The negative one should be on top. The positive one must be at the bottom. Otherwise, shisampam. You understand? So at the moment, it says in which direction should the electric field. Remember, the force is due to the direction of the electric field here. So what we can say, the electric field must be directed upward. That means we reverse the order of these plates. So 8.5, we can say it must be upwards. Okay, that's easy 2 marks. Not a big deal. It says for the ball to remain stationary, the magnitude of the of the electrical force needs to decrease. Explain. Yes, it has to decrease because we could see that the electrostatic force here is 8 times 10 to the exponent minus 4 newtons. But what is the weight of the object is 2, which is less than 8. So it's less than by a factor of 4. So essentially it definitely has, because these two, for this to be stationary, the electric field upward must equal the electrostatic force. I mean the weight downward. So that's the reason. So we can say here in 8.6. So these are the questions that demand a bit here. It says now we need to explain this. The magnitude of the electrical force needs to decrease. Explain. Yes, we know that the electrostatic force Fe, maybe let's write it in words. The electrostatic force Fe now has to oppose and equal the magnitude of the gravitational force. Fg, which is equal to 2 times 10 to the exponent minus 4 newtons. We can say since the Fe was initially 8 times 10 to the exponent minus 4 newtons, it now has to drop to 2 times 10 exponent minus 4 newtons to keep the ball at rest. Oh, isingesi bantam. Bantam, batsho abantu basemampondweni. Bantam. Bantam. The electrostatic force Fe now has to oppose and equal. Remember, it has to oppose it and equal it. The magnitude of the gravitational force, which has this magnitude. We calculated it. Nice and easy, guys. So it says now, since the Fe was initially bigger, for now to equal this, it has to drop to this value. So that is the explanation, guys. So I would say maybe 2 marks for the first part and 1 mark for the last part. At the end of the day, and doesn't balandon. We've got 3 marks, however you explain this, but obviously, guys, be realistic in your explanations. Don't talk nonsense. Okay, some belief though. We don't like babblers here. You need to mean what you say and say what you mean. Obviously, guys, for this to be the case, the plates need to reverse. And secondly, we need to change the potential difference because the force by the electric field strength need to change. So that means the potential difference would also have to change, right? Right. Now it says, how will this influence the required potential difference? It has to do what? Decrease as well. So we know that the potential difference well, masibhale kahle singesi. Singabhali inyaka bhala amasongololo. The potential will have to also decrease. Since, what do we know? From these formulas, remember, F is equal to QE. F is equal to, remember now this is electrostatic force. The Q is the same, but the E is voltmeter over distance. Right. Now, obviously, the distance was not changed unless somebody said it. So we can assume that the distance was kept the same. But I feel like this problem is a bit bad. Assume that the charge on the ball remains the same, but maybe as well as the distance. I'm not happy there. Because if we change the distance, a lot of things can change. Goodness me. Now I'm not happy with this question eventually. You know? I'm not happy with this one eventually. But anyway, guys, well, we knew that from this equation, we could see that the electrostatic force is directly proportional to the electric field, provided the charge is kept constant, right? Right. And we saw that we needed to change the electric field direction as well as its strength. Because we didn't talk about distance, the assumption is that the distance is also constant, as well as Q. So the governing equation here becomes the electric field, the electrostatic force is going to be Q over D times V, where this is a constant. So always simplify these equations so that you can read these things. And remember, if we're saying this guy drops, they are directly proportional. That one will also drop, provided the charge and the distance is kept the same, because there was no mention of this. So be very careful on how to answer these questions, since we know that the electrostatic force is directly proportional to the voltage, provided, hey guys, you need to be careful, charge Q and distance D are kept constant. If you don't mention this, you are dead, okay? So the potential difference will have to decrease, okay? And now you're providing a realistic explanation that this is like this. And we know this from here, but we don't need to say it. We can just say it now because it is realistically so. But this statement here has to come in for the second mark. If you do not mention this, folks, you are dead, okay? Seriously dead and to be buried. Okanye siyakremata futhi, just to show uba siqhela kakubi noba sofile sikufisa some more sikutshise. Anyway, guys, I hope you understood. You can see that this question is nothing but electrostatics. As much as this is a bit of a different scenario, parallel plates and stuff, because these are not being taught, probably this would sound a bit foreign, and maybe some of you would be tired, but I can assure you guys, be very careful of ignoring certain things. Because as much as this may not be taught, but someone may tell you the electric field strength is so and so, okay? And they can give you the information about the proportionalities involved, like this one right here. And then they can pop these questions as a higher grade type of question. And then you're like, what the hell? Yeah, man. So now I've shown you. So you will survive if that happens. But obviously, it's unlikely. But you never know. You can never say never in physical science. Okay, guys. Let's do the last question. I have taken this too long. I need to take a shower and sleep. You see, guys, I'm working hard like I'm doing metric, and you guys are doing metric, but you're relaxed. Now, question 9 says, in the two circuits represented below, the same battery is used. If we're using the same battery, means same EMF. And that means same internal resistance R. So this is very important. So guys, understand information given. Okay, it says now the EMF of the battery and the internal resistance R are unknown. So if they are unknown, these are potential questions. So keep that in mind. Keep looking for ways in which you can answer this question. Okay, so again here I need to make some adjustments. I don't know, this thing has a tendency to, I don't know, man. It just loves to mess with me. Sometimes it comes out nicely, sometimes it disappears. It's not consistent. It irritates me. Believe me. This inconsistency kills me. Okay, that is the case here. This is supposed to be something like that. Yeah, but anyway, whatever, guys, whatever. This thing is supposed to connect here. Don't know why it's not connecting. Okay, now we connected it anyhow. Let's deal with the problems quickly. So we are told here that with 3 resistors, 4, 10, 20 are connected in parallel. Now we can see that. And this is essentially the total effective external resistance. And what do we see? The terminals across the battery is 10 volts. So this is V external. Okay, this is the external voltage. In fact, we can even call it V parallel, because it is the total voltage for this parallel connection, because there's no other voltages elsewhere in series. So this would be the total voltage of the external circuit, and it is effectively V parallel. Okay, now what do we know? The longer thing is the positive terminal, the shorter thing is the negative terminal. Okay, so the current comes out like this. Conventional current comes from the positive, runs down the circuit. At this node, it splits into this component, this component, and let's look for another color there, in that component. Okay, and then in this node, they come together again as the total current, and the circuit is complete. Okay, on the battery. So it is very important to look at the flow of current, conventional current. Okay, looks like here we need to make some adjustments. I thought at first we had everything under control. Now all of a sudden we don't. This thing needs me to draw again. Whatever. Alright guys, the same thing. Conventional current comes out of the positive terminal, which is that longer bar. The negative terminal is the shorter bar. And then it goes through this resistor, completes the circuit nicely. So that's it. Easy. And we can see that this is in series. And when we see this one in series, what does it look like? 11 volts. Can you see? When this was in parallel, it was 10 volts. When this is in series, it's 11. So it's increased because it shows that this effective resistance is greater than the effective resistance of those parallel connections. Nice. So this is nothing but Ohm's law in a way. Okay, so these are connected in parallel as shown in figure 1. Great. The voltmeters reads 10 volts here, and the parallel combination is disconnected, and instead a resistor of 5.5 ohms is connected. So we're taking the same battery and taking it out of here, and we're just inserting it into this circuit as well, and then this is what we see on the voltmeter. Okay, not a problem. Now it says the voltmeter reads this value there, and we've already seen it. Okay, nice, easy, sweet. It says calculate the effective resistance of the 3 resistors in figure 1. Okay, that's easy. So 8.1, we know that 1 over R parallel is going to be equal to 1 over R 4 plus 1 over R 10 ohm, 1 over R 20 ohm. Okay, this implies that 1 over r parallel is going to be 1 over 4 plus 1 over 10 plus 1 over 20. Now this means 1 over r parallel is equal to, we look for the common denominator, and can you see 20 can actually accommodate itself and those two, so this is 20. Now 20 divided by 4 is 5, 5 times the numerator is 5, plus 20 divided by 10 is 2, 2 times the numerator is 2, 20 divided by itself is 1, 1 times 1 is 1. Wow. Now we do the things that can be done. 1 over r parallel is equal to 5 plus 2 is 7 plus 1 is 8 all over 20. Then we cross multiply here and sort this thing out. You can say therefore r parallel is going to be this one swapped around. Okay, let's deal with it. So this is going to be 20 divided by 8. This is 2,5. Can you see? It's definitely half of 5,5. Maybe not even half. It's way less. Sorry. Okay, now this question is not too big, guys, because this is nothing but formula and then substitutions. And the rest of the gymnastic is nothing but mathematics, but must remember the unit. But now, why are we getting 5 marks here? I don't know, guys. I really don't know. So don't ask me why. So, probably this gymnastic, maybe that gymnastic extra mark. I don't know if it is necessary though, because cross multiplication and dividing is the same as finding the common denominator. It's really not a big deal. But hey, the examiners are just throwing marks here, because at some point they're saying, guys, if you held on until the end, even if you didn't answer this at the end, we need to reward you with some 2 extra marks, because this is effectively 3 marks. 5 marks was just a gift from the examiners. So here you're just being showered with 2 extra marks. Explain why the voltmeter reading is, or in figure 2, is greater than in figure 1. Now you see, this is a real higher grade question. Now you have to consider what is cooking, and you can see the effective resistance is small for the same EMF, and for the same internal resistance, right? So now if we have a lower effective resistance, the current will be higher. If the current is higher here, what does it mean? It means the lost volts are going to be more, therefore we'll have less for the external circuit. Whereas here we increase the external resistance, then the current will decrease. If we decrease the current with the constant internal resistance, it means we're also decreasing the lost volts. If we decrease the lost volts, then we're taking less from the EMF. Then there will be more for the external circuit to cover up the more on the resistance. Can you see? More needs more. So we adjust things so that they become more and more and less. You understand? Interesting. So now you heard the explanation, guys. Do I need to write it down? Well, this is a memorandum that you probably want to use as a reference at some point. So let's just do it. We can say in 1, in figure 1, the effective external resistance is less than in figure 2. This is obvious. This is 2,5 against 5,5. And that is the first bullet. What does that mean? This implies that the total current in figure 1 will be more than in figure 2, as explained by the Ohm's law. V equals IR. Okay. Although this is not the best representation, basically I think the best representation, Ohm's law actually talks about the current being directly proportional to the voltage at constant resistance. Essentially. Perhaps that's the best way to express the Ohm's law. The other one is an adjustment. It's not the Ohm's law. The Ohm's law is this one. It says the current directly proportional to the potential difference when the temperature is kept constant, and the temperature affects the resistance. The higher the temperature, the more the resistance. The less the temperature, the less the resistance. Right? Right. For example, think of a heater. A heater offers a higher resistance when you connect it to electricity than the wires that transmit energy. I mean, if you can hold those wires, they're not that hot. You wouldn't burn. But if you hold a heater, you burn, right? Yeah, you understand most of these things. You can just even explain it to yourself, even outside the textbook, if you didn't get it from the textbook, right? Right. Now, can you see, we are even providing a reason why the current drops. Now, we have to come to the second bullet point. We can say since EMF and R are constant, we can say the lost volts in figure 1 will be more than lost volts in figure 2, right? As explained by this one. EMF is equal to essentially I taught V external plus I taught R internal. And remember, if this formula is applied, you will understand that, thankfully, in figure 1, the current did what? Increased. And it increased. So if we're looking at this parameter in figure 1, with the same internal resistance, if we increase the total resistance, the lost volts increase. But the EMF is constant. So this means this product becomes less, because this one has increased. And in figure 2, we'll notice that the resistance increased, and that means the total current dropped. So in figure 2, we see that the current actually drops. And if it drops, what happens? The lost volts drop. If this drop, effectively this product increases, even though the current drops, but that one increases. So can you see? Because the EMF and the internal resistance are constants. Uyibona ke ngoku bafethu, niyibhekile ne? Niyibhekile, sengiyabona ukuthi niyayibona. So these dynamics are best explained by the EMF equation. Otherwise, Ohm's law would confuse you to no answer whatsoever. Because with Ohm's law, you will see that V is equal to IR, right? So essentially, we know that V is IR, but now I is decreasing in the other one, and R is increasing. Can you see an increase and a decrease? You cannot really decide what is cooking for V. So this one is not helping. So you can't use Ohm's law for the explanation of the final answer. But the Ohm's law comes in to explain the issues of the current against resistance. You know, stuff like that. So now this means, therefore, ayibafethu siyaconclude ke manje. Okay, masibeke as a bullet. Singathetha ukubhanga. Now the bullet says now, therefore, the V external for figure 1 is less than V external for figure 2. Okay, nice. Now you don't need to say too much. You stop right there. Because you could even explain that because we're taking less from the same EMF on the other one, while we're taking more from the same EMF from another one. But if you just write the equations that govern some of the explanations, there's 4 bullet points here. So if you like, you can just give each a mark, because these are comprehensive bullet points. But the conclusion was already saying or given. So perhaps not really that big, but maybe the marks are on those 3 bullets above. Who knows? I don't know. But hey, it is what it is. However those marks are distributed, you get them. 9.3 says, calculate the reading on the ammeter A1. Now ammeter A1 is the total. This is I taught in there. So this one is a bit tricky because this is a 4-mark question. So now we need to be strategic. First of all, we know the effective resistance, we know the effective voltage for the external circuit, and that gets the total current. So this one is an easy one. So Ohm's law says V equals IR. This implies that 10 is going to be equal to I taught times the effective resistance is 2,5 for that parallelity there. So this implies that I taught is going to be equal to 10 over 2,5. Therefore, A1 is going to read 10 divided by 2,5 is 4. So this is 4 amperes. Nice and easy. So formula, substitutions, answer. I'm not too sure where's the extra mark again, guys. So I don't know. Maybe we get a mark for choosing that instead of any other thing we can imagine. I'm not too sure. But sometimes the examiners had to give a gift as well for just participating in there. You can see this is a standard grade question. Nothing higher grade about this one. Second question says, calculate the reading on the ammeter A2. Now this is a slightly higher grade question because now A2 is on the other side. No, not really. Not really. Similar question. V equals IR. Now the V is 11 equals I taught, into R, which is 5,5. This implies that I taught is going to be 11 divided by 5,5. Therefore, A2 will be 11 divided by 5,5 is 2. So this is 2 amperes. And what did we say? Didn't we say it? You see, these calculations are just proving the same. I mean, this is again a gift because look at this thing. It's ridiculous. Substitutions, answer. Even that question was 3 marks. But again, examiners found a way of just awarding marks. This is again another standard grade question. But just to prove the point, we just put forward up there. Calculate the internal resistance of the battery. Now, this is a typical higher grade question. In fact, don't expect questions like these ones. These ones are a little bit of an insult to a higher grade question paper, to be honest. Do not expect it. Even this one for 5 marks, please don't expect it. This is 3 marks. All right, good. In fact, this one and that one are not typical of higher grade questions, but again, each paper is unique. Some question papers have some bit of an ease because they realized, can't punish them forever. At some point, we have to give them something. Can't go and fail, right? So this is to prevent a fail, guys. Otherwise, a high grade paper, when it is set properly, a fail could easily be gotten, could be achieved. An embarrassment. Hey, o0 ke sasibachatisa thina safundo sub A. Kwakucula mntakaba usijikeleza iiclasses zonke, wonke umuntu abone uba niyatshata. So funeka uphakamisa izandla. Usually xa kufana nentombazana ababhedile bathola u0 siyabatshatisa. But besingabatshatisa abafana because yeah, sizenze zonke ezibhedayo. Anyway, guys, calculate the internal resistance. Now, this is a typical higher grade question. As you can see, yep, akuzodlalwa ke ngoku. So, umdlalo uphelile. I think question 8.2 and 9.2. Then you know 8 up. 9.2 and 9.5, yeah, are typical serious problems. All right, guys, so what do? Well, we know that the EMF in figure 1 is going to be I tot into R external plus the internal resistance. Now, we were told that the EMF is unknown, so this implies that the EMF is equal to the I tot. What is the I tot in that figure 1? We found out it is 4 into R external was 2,5 plus R. Okay, great. So we can make this one equation 1. And then we know that also the very same EMF in the second scenario was, now this one was 2 into 5,5 plus R. This is equation 2. Can you see both these equations are defining EMF? Okay, it's a weakish higher grade question, to be honest. Okay, maybe let's do this. We can say then we understand that 4 into 2,5 plus R is equal to 2 into 5,5 plus R, because each is equal to EMF. I mean, there's many ways of dealing with simultaneous equations. One can say substitute 1 into 2, wara, eliminate, you do whatever you like, or use reasons to say this is logically the case. Okay, guys, not a big deal. So I can divide by 2. This means I've got 2 into 2,5 plus R equals, now this is 5,5 plus R. So what did I do? I just divided throughout by 2. It's a common factor. Now I distribute. 2 times 2,5 is 5 plus 2R is going to be 5,5 plus R. So what do we see? We take R to the other side. Therefore 2R minus R is going to be R. 5,5 minus 5 is 0,5 ohms. Nice and easy, okay? Nice and easy, guys. So obviously, guys, you get a mark for these two. Equating them is a mark, and getting the answer. Again, you can see that this is effectively nothing but a 4-mark question, not 6 marks. But then, ndizamucinga ke ngoku iphi enye mark andazi, guys. So this is 4 marks. So guys, I don't know. Yabona-ke zii-questions ezinje ezindihlanisayo. Sometimes zenza into endingayiqondi, but ke we can say, whatever. Substituting those different currents, maybe, is the extra mark. Again, you can see the 2 extra marks there again. Is a gift by the gods. Ne? 9.5. We need to find the EMF. Now we can choose any one of our equations. It's going to be 4 into 2,5 plus 0,5. Now let's find the EMF. So we've got 4 into 2,5 plus 0,5. So this is 4 into 3, which is 12. Okay. So this is 12 volts. Alright, so this is as good as just substitutions and answer. The extra mark again, I don't know which develop. It's the gift from the gods. So here they were just generous. But you can see throughout this paper, they have been mostly generous. And that's why. 25 marks for a total of 200 marks. Okay, guys. This is the grand total of 200 marks. So folks, this is the end of our question paper, and yeah, you can see some questions were interesting, some questions were not necessarily that interesting, but at the end of the day you could see your mind was forever at work. And like I said, look at the MCQ questions, compare with the long questions. You'll understand why doing MCQs first is the best thing you can ever do for yourself. And make sure you give a bit of time while your mind is still fresh, because those questions can easily not make sense. But if you use them as a leverage to go and kick those long questions, the long questions might actually remind you of how to deal with the ones that you cannot deal with, because these are interconnected. So I hope, guys, you enjoyed the video, and you're gonna give it a thumbs up, and that provides you a bit of a comprehensive revision session that I hope has improved your thought process and your ability to deal with things. And again, please pay attention to specific papers. If you're writing the paper that you're going to be writing, make sure you have read through this table and you can see exactly, especially things like these. These ones, the constants, are important because they can decide otherwise. They know you know what is right. But to make the examination spicy, they can actually write anything here. And if you are found wanting, this is why cramming is not a good idea. You have to use flexibility of understanding, not flexibility of ignorance. Okay? All right, guys. I will see you some other time. Let's wave our goodbyes. It's been a long review, but I hope it was meaningful in actually shaping your way of doing things, and also using your knowledge at best. At some, you can see here that at times, I don't necessarily use the knowledge that is dictated anyway, but I just combine whatever makes sense at a given point, because you can never know every scenario fully. But if it transmits a particular message, it supposedly is sticking to that kind of a field or a branch of your subject, and you just kick it to the ground. And I can assure you, you will not be wrong. Obviously, this paper is slightly different from the papers you write, but you can see most of the questions are similar in a way. But now, we'll probably do some papers that are now at your level, or should I say in your curriculum, because these questions are not far-fetched. You can see even the tricks are not that bad, but it depends. If paper 1 is easy, paper 2 gets a bit complicated. If paper 2 is complicated, if paper 2 is easy, then paper 1 becomes a bit of a stiff one. So you just have to dance with that, because they normally don't tie them both. Because the idea is to not embarrass a student with a very bad mark. Even if they fail, they must not fail with a 0. And they must not be demoralized as well. They need to see the reason to pick up again and do it again. All right? because we're not here to destroy people's confidence or to destroy their futures, but it's to say you're not doing enough. Please do more. You can do it. All right. Anyway, guys, goodbye. I'll see you some other time. Ciao, ciao.